Good morning. Welcome to day 2 of the second Alaska Sustainable Energy Conference pre-event workshop for 2024. I'm Brittany Smart, the Energy Transitions Initiative Coordinator at the Alaska Center for Energy and Power, which is the primary sponsor of this workshop series. I'll be your MC today, and thank you so much for joining us. Yesterday, we had folks joining us from various countries, from Canada, Germany, Iceland, and even Nigeria. Pardon me. We also had participation from across the lower 48, including Colorado, Delaware, Massachusetts, Minnesota, New Mexico, New York, Oregon, South Carolina, and Virginia, and of course, all across our great state of Alaska. For those of you that missed yesterday, this workshop will be available online in the next week or so. Please keep an eye out on the Alaska Sustainable Energy Conference website for the recording. This is the second in a series of 3 virtual workshops. They are being held monthly as 2 half-day Zoom sessions, free of charge, leading up to the Alaska Sustainable Energy Conference, which is taking place in person from May 20th to 23rd at the Denina Center in Anchorage, Alaska. The purpose of these workshops is to take a deeper dive into specific topics that are of current relevance to the energy opportunity and challenges facing Alaska today. This is the 3rd year that ACEP has hosted these workshops. We bring in some of the top experts and practitioners together to share information and their perspectives on issues that are of interest as we work towards Alaska's energy future. All of the workshops are recorded, and you can find them on the Alaska Sustainable Energy Conference website. Previous topics have included nuclear energy in Alaska, ocean and river energy, hydrogen, low carbon energy transitions, carbon capture and sequestration, and energy storage. We have posted the link in chat in case you'd like to revisit any of those topics. For this year's workshops, we took a different approach. Rather than focusing on different technologies, we look at the broader picture of our energy system. Last month, we focused on utility decision-making, navigating constraints, innovating for the future. We heard from utility leadership and independent power producers on their approach to innovation. We learned how they are balancing their current needs with future imperatives while contending with the constraints of governance structures, regulatory frameworks, and legacy technology investments. For this workshop, we are focused on transmission and distribution, the clean energy transition secret weapon. We will hear different perspectives and approaches regarding how our energy transmission and distribution systems are critical aspects of energy infrastructure and are essential for driving sustainable change in Alaska's energy future. We'll hope you'll join us again next month as we consider betting big, investing in emerging energy, where we will explore hot topics like hydrogen, grid-forming inverters, and artificial intelligence as promising players in the grid of the future. We hope most of you will join us for the Alaska Sustainable Energy Conference as well. Both in-person and virtual tickets are available for the conference, and we hope you'll consider joining us for this event. You can purchase those tickets now at alaskasustainableenergy.com, and the link, again, you can find it in the chat. Following today's program, we'll also be sharing a feedback survey to gain your feedback on this workshop. Everyone who completes the survey will be entered to win 1 3-day conference ticket to the Alaska Sustainable Energy Conference, either in person or virtual. So stick around and be sure to get your short survey submitted. Yesterday, we learned about Iceland's approach to establishing their ring grid, recent research findings about how the rail belt can integrate renewables into the transmission system, managing variability from an IPP perspective, and integration from a utility planning and transmission asset owner perspective. Today, we're going to build on the conversation to learn more about MVDC interties and to talk about rail belt hot topics. Mari Shirazi will moderate presentations from the Alaska Village Electric Cooperative, Resilient Power Systems, and NANA Regional Corporation. After the break, we'll come back and have presentations on transmission planning and grid resilience and innovation partnership, also known as GRIP. Closing us out will be a conversation between Gwen Holdman from ACEP and Andrew Jensen from the Office of Governor Mike Dunleavy regarding ideas and actions being considered at the state level. Now, let's kick off today's event with an activity. We'd like to start off our workshops with some polls for the group. Yesterday, we asked the group in one word, what is driving our current energy transition? And we got some really interesting responses. So as you can see on the slide, the biggest drivers from our participants were really cost, climate, and reliability. We're going to ask some more polls today. To participate in today's polls, please go to your computer and type in pollev.com/TOTTAK216. We recommend using Google Chrome for the best results. And the link to the poll is also in the chat. You can also participate by phone by texting TOTTAK216 to the number 22333. You will receive a text message once you've joined the session. Type and send your responses, and the results will pop up on the next screen. And we will start popping that up on the screen now. So I'd like to give this one a minute to make sure everyone has a chance to participate in our poll this morning. And the question we're going to be asking is, what do you think is the most important emerging energy source or technology for Alaska in 2050? If you joined us last year, this may sound familiar, as we asked a similar question then. We are curious if your ideas have changed over the last year. So again, our question today is, what do you think is the most important emerging energy source or technology for Alaska in 2050? Looks like wind and nuclear are topping our list. Oh, and storage, excellent. Hydrogen, we're getting a lot of great results in this morning. Geothermal, hydrogen, a lot of talk about hydrogen these days. Tidal, nuclear, storage, and wind are definitely topping our list here. Still have a few more popping in, so we'll give it another minute for a couple others to type in any answers. All right, I'm not seeing any shifting. All right, that is, thank you. That is really helpful. We wanted to see how this compared to last year. So keeping in mind that nuclear, storage, and wind were the top responses last year, we see nuclear, solar, and wind as our top responses. So it looks like storage has bumped up in terms of considerations and topics this year. So that's interesting to see that shift. A lot of similar answers. All right. Well, thank you so much for participating in those polls with us. We do like to keep these events engaging. So with that, I'd like to cover some housekeeping items. First of all, please take a moment to introduce yourselves in the chat. Let us know your name and the organization you're from. If you are having any difficulties with audio or trouble viewing the presentations, please send a chat message to event support for assistance. During the workshop, all attendees will be muted. Please submit any questions you may have in the chat. Our moderators will collect and curate those questions to be used during the Q&A portion of each section. The recording of this workshop will be available on the ACEP website at alaskasustainableenergy.com at a later date. Please continue to check back for more information. We're glad that you're here with us live today. To start us off, we're going to be learning about MVDC interties. Please help me welcome Mari Shirazi, who will be moderating our first panel this morning. Good morning, Mari, and thank you so much for joining us. Could you take a moment to introduce yourself and your role here at ACEP before introducing your panelists?
Sure. I'm Mari, and I am research faculty here at Alaska Center for Energy and Power. I am a UAF grad. I'm proud to be a UAF grad from a long time ago. And then I spent 20 years or so in Colorado working at the National Renewable Energy Laboratory. And I'm happy to be back in Fairbanks. My interests are largely power electronics or bridging power electronics and power systems, as that is what's happening today in our grids. Today, I am super excited to have a wonderful group of panelists to talk about medium voltage DC interties. So intertie / transmission lines are getting quite a lot of interest today, especially there was the recently announced in February, DOE announced what they call this transmission facilitation program. And it's not a grant, but it's a loan program, and it specifically calls out connecting microgrids in Alaska, Hawaii, and the U.S. territories. So this is a hot topic nationwide, and it is not something new up here. There are people, including people on this panel, who have been looking at this for many, many years, interconnected communities and possibly using medium voltage DC. So what we have gathered today, we tried to get some various perspectives on this. We have, I'll just give a very brief overview of what folks are going to be, or who the folks are and what they'll be talking about. We have Sunny Adams, who's from Atochican, which is NANA's public benefits company. And Sunny is going to provide a regional perspective, both as a community member and a landowner in the Northwest Arctic. We have Mehdi Abul Hassani from Resilient Power Systems. Mehdi will provide a vendor and more importantly, a technology developer perspective. He'll introduce the medium voltage DC converter technology and discuss state of the art and applications. And then we have two people from providing utility perspective. We have Darren Westby from Alaska Village Electric Cooperative. He will discuss design criteria specifically for in broadly applicable, but with the specifics of an intertie between Shungnak and Kobuk, an MVDC intertie Shungnak and Kobuk, which actually has been funded by a recently awarded grant from the Office of Clean Energy Demonstrations. And we'll hear a little bit more about that from Sunny as well. And then we also have William Thompson from AVEC as well. And he will continue the utility perspective and provide some more detailed discussion specifically on a couple topics that are critical. One is cable versus overhead transmission, how you make those kinds of decisions, and then also discuss how control aspects change when you have an MVDC intertie on how power flows are controlled across the DC network. So that's a nutshell of the panel. And I'm going to kick it off by, actually I should say, so the order is we're going to start from the top level from a, customer/community and landowner perspective, and then we're going to dive down and go from the bottom up. We're going to go down to the nitty-gritty details and then move up to utility planning and engineering. So we're going to kick it off with Sunny Adams. And Sunny has worked at NANA Regional Corporations for the past 16 years in various roles, managing and directing projects and technical oversight of the Red Dog Mine, the NANA Gravel Program, and shareholder development. Since 2008, Sunny has been the director of the Alternative Energy Program, overseeing the successful wind, solar, battery installations that are happening right now across the region, as well as other energy efficiency and cost reduction initiatives. I like that Sunny was born in Fairbanks and was raised in Kotzebue, and he's worked as an operator and metallurgical engineer at the Red Dog Mine and graduated from Montana Tech with a degree in metallurgical and materials engineering.
My name is Sunny Adams. I'm the Director of Energy for Atochican, which is a public benefits company. I've been, working on energy projects with the Northwest Arctic Borough, Deer Stone Consulting, KEA, for a number of years, along with our tribes in our region. So next slide, please. So this is our region. It's 36,000 square miles. We have 11 villages, 11 tribes. The only mode of transportation is by plane, snow machine, or boat. We have one existing intertie, and that's between Shungnak and Kobuk. We've got 5 microgrids within the region right now, and it's 61% more expensive to live in our region than it is to live here in Anchorage. We have the second largest zinc producing mine in the world called the Red Dog Mine, which is located near Kivalina. Next slide, please. So this here is a graph that I received from Ingomar, the Northwest Arctic Borough. It's the prices for 2023. As you can see, our fuel prices within the region are extremely high. Right now, These are 2023 prices. Right now, they range anywhere from $8 to $18 per gallon, and it's putting an extreme burden on a lot of our residents in our region. Part of the reason is we have to fly in fuel into some of our villages, specifically Noatak and the Upper Kobuk villages. And these high fuel prices are having an extreme impact on our electrical rates. If you look at the columns to the right, you can see our electric rates with and without the state subsidy. If you go over 750 kilowatt hours, your fuel prices, I mean, your electric rates are going to go extremely high. Yesterday, I saw a cousin of mine in Kotzebue, and he said that his monthly bill was like $764. And so fuel prices are having extreme impact on our region's economy. Next slide, please. So this is our project timeline. You know, we've been working on energy projects since 2008. Just some highlights from this roadmap to lower the cost of energy. You know, we created our energy steering committee meeting, which you know, KEA, Northwest Arctic Borough, Deerstone, and all of our tribes and our stakeholders within the region participate in this meeting every March and October. And so a lot of the work that we've accomplished, like diesel generator off operation and moving towards solar and batteries, you know, talking about heat pumps, all of that information was gathered at these meetings over the years. And we recently received a DOE OSED grant, and now we're going to expand those microgrid projects to all of the region. One of our priorities is workforce development and capacity building, and that will be addressed in the coming years. Next slide, please. So one of the things that, you know, I know this is about Energize, you know, we need to talk sort of about the sources, some of the projects that we're working on and some of the needs. This graphic below in the bottom half is a microgrid out in Deering and Buckland. And we were able to achieve diesel generator off operation in the summertime when you have plenty of wind, plenty of solar. And our thoughts is if we can lower our electric rates, lower the amount of electricity that we use, get to low cost electricity is what I'm talking about. And then we can start installing heat pumps in the home. Under the DOE OSED grant, we're going to be installing 858 heat pumps throughout 10 villages. And that project is going to start up within the year. But the only reason we're successful at all of our projects is because of the partnerships and the collaboration that we created over the years. I mean, it's been USDA, Department of Energy, the state of Alaska, our tribes, all of the vendors working together. That's one of the reasons that we're successful. Next slide, please. So there are challenges with the work that we do when anytime you're trying to do a microgrid build out or you're installing a transmission line. There are some challenges. I mean, it's far more expensive to do projects within the Northwest Alaska because of the high fuel costs. There are some concerns on out-migration. If more people leave the region, you're going to create more of a burden on the people that stay because your fixed cost to operate that power plant remains the same. Workforce development, we need succession planning of energy champions. We see a small group of people getting ready to retire, so that needs to be addressed. Climate change is self-explanatory. We're seeing erosion. Our power poles are leaning. We also believe that our energy subsidies continue to be threatened. Power cost equalization is always under the microscope, and on people how trying to reduce it or take it away, I think that's definitely a concern. Remote communications to microgrids off the road system can be challenging. That's something we're working on through a broadband grant that we received, so I'll be addressing that later. And one of our main concerns right now is the power plant upgrades that are needed in the villages, especially when you're building out a microgrid project. It costs $1.6 million per village to do those upgrades to integrate renewable energy. Next slide, please. So getting to the transmission line, it's definitely something that we want to do. We want to replace the transmission line between Kobuk and Shungnak. They're working on scheduling the geotechnical work along with the design, looking at procurement, logistics. But there's other opportunities that we see coming in the future. I mean, this NTIA broadband grant that NANA received, $65 million. We feel like that if you can combine projects, you might be able to add another transmission line between Ambler and Shungnak. Like I said, it's having to fly in fuel into those Upper Kobuk villages is really expensive. So if you can mobilize and then bring a fiber line along with a power line, I think there are synergies there to help reduce the cost of energy. Transmission lines are vital to promoting economic development and energy security. This has been a long-term goal of the Energy Steering Committee meeting. It's something we've been spinning our wheels on. I think we have real opportunity to make that change soon. Back in 2014, we did a Cosmos Hills feasibility study, and the streamflow data has shown that we can generate power and heat for Kobuk, Shungnak, and Ambler 8 months out of the year. So if you put in the transmission line between Ambler and Shungnak, then you can serve those 3 villages with power and heat. One of the things that came about through the Energy Steering Committee, along with the Northwest Arctic Bureau and Deerstone Consulting, as we came up with a concept through thinking about a joint action agency, but it also led into creating these independent power producers within the villages. And the way PCE was set up is if you reduce diesel consumption through renewable energy, you reduce that power cost equalization. So we found a way to recapture that. What you do is you create an IPP and then you turn around and sell that power to the utility. And that's an eligible expense of power cost equalization. So that's one of the things that's one of the ways we see that, we can keep more money in the village, we can keep more money in the region, and we can keep more money in the state. Next slide, please. Thank you. That's all I have for today, and I'll pass it back to Mari.
Great. Thank you so much, Sunny. So we had planned that we would have everybody talk and then we would have a combined Q&A at the end. I forgot to mention that earlier. If you type your questions into the chat, then we'll take note of them and then we will add them at the end. And if you would like to address them to specific people, you can indicate that in the chat. Okay, so next we started high, and I forgot that Sunny actually also, in addition to community member and landowner, is also providing an IPP perspective. So that's cool. He wears a lot of hats. Now we're going to dive low into technology with Dr. Abul Hassani. And Dr. Abul Hassani is currently the Chief Technology Officer and co-founder of Resilient Power Systems, where he leads the development of solid-state transformer-based DC fast electric vehicle chargers. Dr. Abul Hassani received his PhD in electrical engineering from Texas A&M University and has held key roles in prominent organizations, including Toshiba, University of Houston, TECO Westinghouse, and General Motors. Dr. Abul Hassani holds 35 U.S. and international patents and has authored several book chapters as well as numerous journal and conference papers. So we are looking forward to hearing about converters. Take it away.
Thank you very much, Mari, for introduction. Today, I'm going to talk about advancement in MVDC power converters and their impact in the power grids. There is a new topic that has been initiated by modernization of the grid, and that is solid state power substation. In old or conventional power system, there were few power generators. There are, and then there was a transmission line that transferring the power to the load centers. But in new grids that we see a lot of new loads and a lot of new uh, generation source, such as PV, wind turbine, hydrogen, that has been distributed along the grid. So those are needing much more flexible control. So the power flow can be bidirectional, and it caused a lot of problems in power grid because now you have multiple source of generation that they can contribute to the active power and reactive power. Hence, then, so that's a new topic has been created, and that was initiated by DOE, Department of Energy, that now they have a roadmap that basically they are specifying the requirement. So the need for solid state power system is because of all the new power sources, and also because of the new capability that power electronics converter can provide. So one of them is basically a voltage support, reactive power compensation. So it can create a lot of impact in the grid by increasing resiliency, efficiency, and improve flexibility and security of the energy. So they are used for high voltage direct current or MVDC power transmission, integrating renewable energy resources, and also for or basically creating net zero buildings. So that's all included in solid state power substation, and they are working as a multi-port power converter that several loads and several power generation can be connected to that and like work as a power router. In DOE roadmap, what was recognized to make it feasible and cost effective. So they recognize it has to be based on power building blocks or PEB, which make it very modular and make it very cost effective. So just one component, which is the power electronics building block, it is used to build the power converter for higher voltage or higher power. So if you need higher power, we just need to parallel them. And if we need higher voltage, we need to connect them in series. So this make it basically very standard as far as the servicing, and also make it cost effective to have one solution for all different application. Um, so it can be used for different voltage or for different application, and it is scalable and it is modular. So that was recognized on that roadmap from DOE, and that is based on we use actually that as a base for our design. So now about MVDC power converter. So those are converters that they are converting AC voltage to DC voltage. So AC voltage range is from 1 kV to 35 kV AC, and the DC range is from 1 kV to 75 kV DC, and converting back to the AC. So there are several important roles for MVDC power converters in modern grid, which one of them is integrating renewable energy. So they are very efficient in integrating renewable energy, such as solar farms, wind farms, energy storage unit. So most of the solar farms or wind farms, they are remote, and the energy which they are producing, they are in the form of the DC. So it's much easier to transfer DC power from the remote area and send it back to the urban area or the load center. They also have impact on the grid stability and reliability. So MVDC has much better and or easier power flow control. There is no such oscillation that is created by capacitor switching. So when we do capacitor switching, there could be some voltage oscillation that it can peak up to 2 times of the voltage. There could be some resonance in AC transmission, which can because of the inductance or capacitance of the power line or the passive filters of the uh, inverter base generators. So those are eliminated when we have DC power flow. So that is used for long distance transmission since we don't have any reactive power flow in the MVDC line. There are less losses. So that's very efficient. Um, the interconnection of the grid. So if there are two grids that they are not synchronized, such as in Texas, so then there are some interties that they are connecting to different grids, or even actually for macro grids. So if we want to connect to macro grids, it's very efficient to use MVDC. And support, of course, they have support for electric transportation, for EV charging, for truck charging. So that's the converter is much easier. And flexibility and scalability, which is inherent in here. So if you want to increase the power, then we just basically synchronize more power converter together, and they can provide more power. So all of them they are synchronized, and so scalability is much easier for MVDC power converter. Here is actually our topology. So the resilient power system topology, which is based on cascading multiple smaller power module. Smaller means lower voltage. So basically we are cascading lower voltage power module together to get to the higher voltage. So that basically helping in harmonic elimination, because power electronic switches, they are either on or off. So they can create zero voltage or they can create the maximum DC bus voltage. But by cascading them, then we can basically do a step conversion basically. So we can turn on them in a step or a staircase form, which basically it's a multi-level power conversion, and it is reducing the harmonics. So that's and all of these power module in our technology are linked through high frequency magnetic energy link. So we don't have any 60 hertz transformers. 60 hertz transformers, they are very bulky, and they are using a lot of material, iron and copper, that now has been recognized as a near critical materials in DOE roadmap. That has been reduced in our design, because when you increase the frequency, all the magnetics are decreased, basically the same ratio. So if you increase the frequency by 10 times, all the magnetics and filtering requirement are decreased by 10 times as well. So the way that this system works, we are converting the medium voltage to multiple multiple DC voltage, and then those multiple DC voltage are converted to high frequency, and then high frequency energy is pulled into the high frequency magnetic energy link. So all of these power modules are linked through that energy link. And if one of those power module needs some energy, they are taking from that pool. If they have extra, then they are putting into the back to the energy lane. So that's the technology. So there are some other technologies that they are based on DC link. So DC link, either they have medium voltage DC link or low voltage DC link, but they need a lot of capacitance. So by doing this, we store energy in the form of magnetic energy link. And so that basically create lower requirement for the capacitance. The technology that we have also include MVDC circuit breaker, which we know actually that's very difficult to get hold of DC breaker, especially at the MVDC. So we have solid state switch that it can act as a protection and also act as a energization. And these kind of power converters, they don't have any inrush current. So we know transformers, they have inrush current, but the MVDC power converters, resilient version, they don't have any inrush current. Advanced power flow control, so which is tailored for optimizing the power flow in the MVDC line. They can work in the harsh environment. The enclosure is weatherproof and totally enclosed, exactly similar to transformer, and they can also work in the flood zone. If there is a flood, they can work up to 2 feet of the water without disrupt in operation, and they can handle surge, voltage transient, and fault right through, and any problem in weather or cyber event. And since they don't have any rush current, they can reconnect very quickly. 2 times of the voltage. They are capable of 2 times of the voltage for 2 minutes, and they can have for our 15 kV class, we have 95 kV BIL, which that's similar to the transformer standard. So there are different applications for MVDC power converters. So one application, as we said, that's integrating remote solar farms or remote wind farms or energy storage to the grid. So MVDC power collection is much easier for this kind of renewable energy sources. So those are very favorite for those kind of application. And most of the wind energy, wind turbines or solar farms are located remotely. So transferring that energy back to the urban area through the MVDC line, it makes sense because it has lower losses. Grid interconnections, so such as interties between Texas and neighboring states, and rural area electrification. That's another application that perhaps Alaska benefit of them. So for rural interties with MVDC extension, there are some challenges and there are some benefit of using MVDC. So there are challenges in rural electrification, which is one of them is limited access to reliable electricity. High cost of extending traditional AC lines, difficulty in integrating renewables, because if you want to integrate renewables, then you need to have power converters, and which they need to convert DC voltage back to the AC and synchronize to the AC grid. But by doing everything in DC, then you are eliminating a lot of equipment and a lot of complexity. So using MVDC, then we have efficient power transmission and much easier integration of the renewable, and we get actually benefit of scalability and flexibility. And there is actually a case study that I guess we heard about that, and I guess we are going to talk more about that. That's from Shangak to Quebec MVDC line, which was funded by DOE. that we are working to provide those power converters. So as a conclusion, so we get benefit of efficiency, which is increasing the efficiency by doing MVDC. So compared to traditional AC system, MVDC power line has lower losses. And integration of renewable energy into the grid is much easier, so it can be seamless, and it doesn't have that those problems that could happen in AC transmission lines, which it could be resonance and or oscillation, voltage oscillation in AC grids. It helps grid stability because they are linked through the DC, then it can bring more grid stability and reliability by providing better control of the power flow and voltage levels. So those problems such as voltage fluctuation and grid congestion are mitigated. For long distance transmission, those are very ideal for long distance transmission. Lower because they offer lower power losses compared to traditional AC transmission when there is actually extended distance. So it could basically improve the efficiency. So in long term, then they are contributing to reducing the losses in the power grid. Flexibility and scalability, that's another benefit of MVDC. So it helps for easier adoption of the grid requirement, changes in energy demand, and integration of the new technology, new renewable energy storage to the grid. Cost effectiveness, so there is actually initial investment, but in long term, MVDC can offer cost saving to reduce transmission loss and improve grid efficiency and enhance utilization of the renewable energy. So make it very cost effective for modern grid infrastructure. Resilient power MVDC power converters, what we can offer is the modularity. So it's very modular. So for expansion, it's very easy. So expansion can be done very easily. They have a port that they can be synchronized if there is a need to add more power. They are scalable, resilient. Our system has a redundant component and it has self-healing function. So if there is one component failed, then automatically that component or that power module is bypassed and the converter started back in operation. So it does self-monitoring, and if there is a health problem or a failure, then it can bypass and continue working. So it's very resilient that way. It provides grid voltage support, such as reactive power compensation, and it offers no inrush current, which we know actually transformers, they have inrush current. So such as the problem in California, that was one of the fire, I guess Canyon fire, that it was caused by PV inverters that one of them trip and then starting back, it requires inrush current, overloading other power lines, and it created that problems. But this system does not have any inrush current. So this is the end of my presentation, and thank you very much for your attention. Back to you, Mari.
Thank you, Mehdi. I will also point out that, when we did this case study looking at an intertie between Ambler and Shungnak, actually, this had been looked at prior to. But honestly, the biggest challenge was finding a technology provider who was able to provide equipment that was, in the voltage and power levels that are relevant for rural Alaska. Most of the commercial products today are much higher voltage, greater than tens of kV, and maybe the minimum size available was 30 megawatts. So to my knowledge, RPS is the only one that provides something that has a commercial product that is in the range that is relevant for rural intertie. So we were lucky to hook up with RPS. Okay, so moving on, we're going to now move to utility perspective, and we're going to start with Darren Westby. Darren Westby, and if I get any of this wrong, Darren will correct me. Darren has been the manager of engineering for the last 2 years with AVEC, where he oversees all engineering aspects for their microgrid power systems that are serving 59 villages across Alaska. Prior to AVEC, Darren spent 30 years as a consultant in Wisconsin, providing electrical engineering services for systems ranging from low voltage to 230 kV, so not unfamiliar with high voltage, and was working to integrate large and small scale renewables. So looking forward to leverage that background and expertise, and I'll kick it over to Darren.
Darren Westby here with AVEC, manager of engineering. Been here 2 years, and prior to that, I was in Wisconsin for 30 years as a consultant, doing various designs, including renewables, solar, rooftop solar, all the way up to large scale renewables. So just to kind of touch base on kind of the drivers that the biggest drivers, and one of them I noticed was climate that people were interested in, that Brittany mentioned. So the Kobuk to Shungnak existing tie line, as you can see on the map here, it needs to be rebuilt due to climate change. The existing steel piles that were installed are jacking out of the ground, and the poles are leaning over. So that this provided a great opportunity to rebuild that line, and then also to take advantage of a new 25 kV medium voltage DC line. So we're just starting to kind of get into the design. For the OSET application, we did some preliminary conceptual designs, and then also looked at prior designs back about 10 years ago, prior to my being here. And now with the new technology that media has presented, it gives a great opportunity for us to move forward on this. So we're looking, we looked at providing a second DC line in addition to the AC line, but that got more costly. So what our intent is here is to utilize the new 3-phase line with standard RUS construction at 25 kV insulation for AC, but we're actually going to use the outside conductors on a flat construction for DC. So I'll use the same conductors, and a couple of reasons why I'd like to stay with 25 kV or potentially even 35 kV is its standard distribution, construction and materials and rubber goods with elbows, cables and so forth that are commonly used in the lower 48 as a distribution voltage. So with the I guess the new technology that RPS has provided at this power level, it provides a great opportunity for us to take advantage of that and not have transmission type converters at 69 kV and above, which are extremely costly. And for the loads that we have typical of our villages, like Kobuk is a very small village with the loads, about 100 kVA or less. So I guess that provides a great opportunity for us to move forward with this, with the converter from RPS. And Mari mentioned on the, as far as looking at different vendors, we looked at, ABB and Siemens, the ones that provide the high voltage DC, but they didn't have any down at this power level. So I guess for Shungnak, on the Shungnak end, there's an existing power plant there, diesel plant with solar and batteries. Now they're directly connected at 480 volt to our plant, and then this tie line at 12 kV currently goes to a standby plant in Kobuk. So on the Shungnak end, we'd have, the intent is to go from 25 kV DC to 480 volt AC, and we'd connect direct to 480 volt right into our power plant with this converter then, and then that would go to the DC line. And then we'd have interlocks and controls, so the 480 volt breaker controlling the 25 kV converters. It would switch on and off based on the control system. It's interconnected at Shungnak, and then what the converter provides. At the Kobuk end, we were looking at different options, different sizes, anywhere from about 250 kW to 500 kW. In the Shungnak end, we're looking at more of the 1 megawatt converter. Couple things on the Kobuk end. Since it's a standby plant, it's very basic. Basically, it's a transfer switch with a generator, and there's a 500 gallon day tank there. So there's no bulk fuel storage at all. So this tie line run at DC would provide normal power, but we wanted to make sure that we had reliable power, since we don't have the 25 kV that's proven yet. So we'd want to make sure that we have that backup if needed, if something were to happen to the converters and so forth. In the bottom part, we also looked at directly connecting the converter from 25 kV DC to 12 kV AC and not go directly into the 480 volt side of the Kobuk end, but that provides, it's more costly to do it that way on the converter end. So we're still looking at different options to interconnect Kobuk at that end. Let's see, go back here. So this here, this is kind of the layout of the switchgear at Kobuk. This is it's new ComApp switchgear with a 480 volt section. So this is what Sunny was saying. It's about a $1.6 million upgrade. That's what has occurred already in Shungnak. And so the idea here is to connect to the 480 volt right into the switchgear through the converter, and then a 25 kV DC line with a backup 3-phase 7200/1247 kV line AC, and then back to 480 volt and tie into the Kobuk plant. Some of the design concepts. We're working with RPS, and they provide fault protection by indicating there's a ground point in the center. So there's 12 kV from positive to ground, and then the negative to ground here. So you get 12 kV on each point, and then on the ground portion, you can have an impedance or a solidly grounded center point for fault detection. And they would monitor that ground wire for voltage and current, and then switch off the converter if there was a fault event, which is good compared to providing a DC type of breaker on the line, which is not. I guess I don't even know if they make one on the overhead for an overhead application. So that's a convenient way to do that, and we want to make sure that works as well. Yeah. So I guess if there was a issue on the DC line, the Shungnak power plant ComApp control would auto restore, and then the 12 kV feed that's a backup would be restored to provide power back to Kobuk. The switches on either end of the DC line would then be isolated and there until we could locate the fault and restore power back on the DC. And that would be a manual. At this point, it'd probably be a manual operation to restore it back to the DC. Then there's additional DC protection on the converters under an overvoltage, overload, temperature monitoring, COM errors, and they'd be integrated into the control scheme. One of the points on the DC line is we want to make sure that there's gang operated switches at both ends to completely isolate the DC line. One of the things we want to make sure of is any devices that are potentially could be opened by a lineman. We want to make sure that they have some key interlocks with the converters, so as we don't open up the GOABs, which are not rated for DC. So the line would have to be completely dead before those could be opened. So basically, this DC line is a proof of concept for future lines between Shungnak and Ambler, as Sunny was mentioning. And on the converter side, they can have different ports on DC. So you could have one converter that would provide a tie to Kobuk. You could have another tie through a different port on that same converter, basically that would head towards Ambler. In this case, we'd probably have separate ones because the first one's funded. The Ambler to Shungnak one is just being looked at now and not funded. And then there's talk about a 1 megawatt turbine just on the other side of Shungnak that would head to Ambler. So one of the ideas is to connect a DC turbine directly to potentially a DC line from Shungnak to Ambler. And this is the output that we looked at. We run some computer models initially, conceptually. You can thank Amy here for doing all the work. But anyways, we modeled it in easy power. And basically we looked at AC and DC options for Kobuk, but then also for future installations with longer distance between communities to intertie them potentially with medium voltage DC. So you can kind of see on the left the miles between villages, and then the various loads from 100 kVA up to 750 kVA, and then basically the conductor size that was modeled. And in this case, we'd use either number 2 ACSR or 1-aught ACSR. That's somewhat common for us for AVEC. We do not have any line trucks, only in 2 of our villages that are larger. They're kind of outliers. But for all the rest of them, lineman, Klein poles, and so forth. So we try to keep things manageable as far as workability on the lines and not get too heavy lines and large poles and so forth. So you can kind of see from here, we did the 10 miles, the 20 miles, and 40 miles. And there's kind of some breaking points. It's kind of a busy table here, but if you look at rows 24 and 25, that's at 40 miles with 100 kVA, looking at the 12 kV option, which is not a great option. And you can kind of see here the engine basically is trying to support the voltage and providing VARs to the point that it can't. And so that's not a great option. So then at 25 kV DC, you can kind of see for 100 kVA of load, the voltage at the end of the line is about 2%, drop. And as you go up in kVA, the 500 kVA with 25 kV, you can see the voltage approaches, about 11% drop. Now the DC voltage can vary pretty significantly and not have a great effect on the power quality. Now, in addition to this, there was a Simulink modeled by RPS. I didn't include that, and Meaty could probably touch base on that, but it was very basic. This was more of the steady state power flow. So in this is just the single line drawing that accompanies the output results here.
Thank you, Darren. I know a lot of people have been really interested to hear about this project, and we're lucky that you're willing to step through a lot of these details. Okay, so our last presenter is William Thompson. And William is a professional electrical engineer in both Alaska and Canada, and has nearly 50 years of experience at engineering electrical power systems and equipment with a focus on digital real-time control system design. His work has mostly been applied to hydro and wind renewable energy and its integration with traditional technology. And Bill's been also passionate about these MVDC interties for quite a long time. All right, turning it over.
Thank you, Mark. I assume everyone can hear me. MVDC really is potentially a game changer for rural Alaska, and I'm going to quickly go through that. I'm going to talk about MVDC and the impact on just this one project that we're talking about here, which is just simply a relatively small, short, 10-mile section of line between Shugnak and Kobuk. And it provides a really good test base for trying out MVDC with minimal risk. So we'll continue with that. Could I have the next slide, please? So this is a pretty generic slide that I show just to orient people on who AVEC is and where we're situated. But there's a couple of items that you can pull out of these statistics. And one is that we have 59 member communities out in rural Alaska. They're relatively small. The total number of residents is 31,000. So what's that? The average is not many residents per village. So we're talking relatively small loads, widely distributed. We have the largest service area for any rural RUS electrical cooperative in the world. But look at this, 59 member communities serviced with 48 power plants, individual microgrid power plants, no interties, almost none. Yes, we do have a few because there's at least 11 communities that are being serviced by power from adjacent villages. But basically, very few interties. And the question you have to ask yourself is why? Well, the answer is it's very expensive, both to install them. The terrain is very unforgiving, and also then to maintain them. For instance, the existing Quebec line that's already been mentioned by Darren is falling over. The whatever H-piles they put into the ground are being jacked out. If they didn't use an H-pile, the poles are definitely falling over. This is tundra, and it's in an area where the permafrost is melting. So just trouble upon trouble. Next. Oh, and that little red circle is the area that contains Shugnak and Kobuk. Go to the next slide, please. So let's talk about Kobuk and how it relates to providing an intertie. So the average load for the first quarter of this year was 90 kW. But if you look at the peak 15-minute loading, it did peak at 168 kW back in 2022. It hasn't exceeded that since. And so that provides a useful target in terms of doing some calculations on the AC and DC characteristics of what the intertie might look like. The other thing that I tried to look at here was using our minimal standard for AC line construction, which is also something Darren touched on, but also repurposing it for DC, MVDC transmission, just seeing how that works in this instance with that load. So we assume number 2 ACSR, that's aluminum conductor, steel reinforced. It has a certain resistance, and we have 55,000 feet of total line that has to be built. Works out the resistance, we know what the current is, and we end up with if this was installed as an AC line using 12.5 kV installation, which is normally our standard, it'd be a 1.5% drop at peak load. This is quite acceptable. There's nothing wrong with putting an MVD AC line in this installation. So why DC? Next slide, please. So looked at the numbers again, and Darren was talking 25 kV, but I do know that the cost of the inverters goes up with the terminal voltage. So I just did a calculation at 10 kVA, kVDC, in order to find out if this standard number 2 ACSR construction would be serviceable. I also assumed that since we had 4 runs of wire total, that we'd run out 4 wires. At 25 kV, that's not possible, but or not necessary. But with 10 kV, I'm trying to reduce the resistance loss. This is straight Ohm's law. This is just DC current going through a resistance causing some heat that you lose. So I did that calculation at just 10 kV DC. and it's only 2.3%. So almost comparable, apples to apples, even though the approach is totally different for MVDC as for MVAC. So this is interesting. We have the opportunity to put a transmission line in and operate it in DC instead of AC. Next slide, please. Oh, and before I go, there's one of the ways to trench in a cable, which I'm going to talk about in a minute. Next slide, please. So again, trying to keep the cost down to start. To use cables, the whole point actually of using MVDC is to be able to use cables. They cannot be used for any appreciable distance at light loads using AC for technical reasons. But you can go almost unlimited lengths using MVDC with cables. And cabling is just about the only way I can see that we can do interties between villages with a lower capital cost of installation and a much lower cost of maintenance, being underground or down or under the water. There's different ways we could put this in. We can trench it. We could put it in a waterway. We can put it over marshy ground where in the spring when it melts it would sink down into the marsh and be lost. Some of these installations do require submarine cable rather than URD, but in terms of electrical characteristics, a URD cable is something that we use everywhere, and it's very well known, it's inexpensive, and it provides an interesting baseline for looking at the characteristics of it using DC. So again, crunching through some numbers. This is just Ohm's law stuff, nothing fancy. If we put a single line of this rather inexpensive URD between Shugnak and Kobuk, we would have a voltage drop at peak load. This non-occurring peak load that we got in 2022, which was 168 kW, we would have 4.6%. So that's quite a bit higher. That's double what we had in the last slide. But you've got to remember that's peak load. You got to remember that that's at 10 kW. If we run the voltage higher, we can reduce this. And since we normally have 90 kW load, then which would only incur a loss of 1.2%, this is acceptable. Yes, the voltage varies, but that doesn't matter so much with MVDC, which I'll get to in a second. Note that the picture I've shown here is not submarine cable. Submarine cable would have a layer of steel on the outside. It would be much more rugged, and you could drive over it all day with snowmobiles, for instance, and not damage the cable. Having said that, it's probably a challenge to some of the snowmobile drivers in Alaska. So I probably need to back off on that a bit. Anyways, this URD is what we've used elsewhere in underground services in Alaska. It's very familiar to anyone in the utility field. Next slide, please. Again, that's another repeat of that trenching mechanism that was used in Canada to install fiber. Anyways, here's the beauty of MVDC. With AC, we have frequency voltage. Those are two bulk variables. We have to precisely maintain both of them in order to maintain the quality of power. But with MVDC, there's only one. That's voltage. Frequency goes away. Frequency is not communicated. It's direct current at a relatively steady voltage. Also, because the end user never sees that voltage, it can vary while the solid-state power substations, which I already mentioned, SSPS inverters, compensate and keep the load voltage constant. This greatly simplifies control because not only do we don't have one variable that we have to worry about, but we don't have to worry about it nearly as tightly as we do on an AC system, where we do have to maintain pretty accurate voltage. Not transmitted over MVDC system. So we don't have to synchronize various sites. We don't have to synchronize generators between villages. Much simpler. So from a controls point of view, now I'm going to talk controls. MVDC is much simpler to control than AC. Much simpler. I was going to do a longer talk about control of an MVDC system, but it's really not necessary. If you have insufficient availability of power in an MVDC system, the voltage drops. If you have a surplus of renewables, then you can push power back into the line and raise the voltage. If the voltage starts to go high, then high cost sources of power like diesel generators can back off. And this is all done without any fancy communication system. This is all done just basically on the voltage that you see on the line. Next slide, please. So load nodes. That's an SSPS site that does not have any generation, simply loads up the MVDC as required to supply its loads. And so it's pulling power from that MVDC distribution system. If you have a generation node, if you have generation, especially, and this is where MVDC comes in to make renewables easier, because more and more of these nodes will stop being load nodes and start becoming generation nodes, at least part of the time. For instance, with solar, high noon in the summer, it's going to be a generation node. Well, the control of those nodes becomes a lot simpler because it is, again, just managed by voltage on the distribution line. If you've got surplus power, you start pushing the voltage high. That will back off on sources of high cost power, and if it goes too high, then the generation sources back off. So yes, there is some control, but intrinsically it's a stable system, and you can apply controls over top of that to take care of short-term issues. So renewable nodes, of course, are allowed to push the voltage higher. And that's the third category there, where not only do you have a generation node, but it's renewable. And at the bottom, supervisor, I'm not saying you don't need to have supervisor communications. It's still necessary to, with a multiplicity of generation sources, you want to run the lowest marginal cost generation source at first at all times. And so that does require some supervisory communications. However, at least it's being overlaid on a system that's intrinsically stable. Next slide, please. And that is my quick talk about MVDC and how it relates to distribution between small villages in Alaska generally, and specifically this Shungnak to Quebec line.
Excellent. Thank you. Thank you very much, Bill, for digging into some more of these details and questions about cable, especially, and control. I think right now we are right on target, and we are going to open this up for Q&A for everybody. And I will start by reading questions that I have received so far. And we will start with, and again, audience, if you have questions, please just put them in the chat, and we will grab them off the list and ask them to whoever you designate or to the group as a whole. Okay, so we have the first question here is for Sunny. Sunny, you spoke about the potential synergy of running both broadband and power between villages, which of course makes sense. Has there been any consideration of including road access as well for a shorter transportation route for the Ambler mining areas than what has been proposed across over to the Dalton Highway? Since mining would also expect significant power needs, this could lower energy costs for all in the area.
Thank you for the question. So several years ago, they were discussing different concepts, different scenarios on how they can bring about the Ambler mine, and I think there was two other routes they considered. One was towards the Red Dog mine, seeing that they have an existing port, and it's already built. I think the other route was towards Kotzebue, seeing that Kotzebue is wanting to build a port to help bulk fuel storage. And so those two concepts were discussed several years ago. I mean, we're talking 10, 12 years ago, and I don't think, it's brought up as of lately.
Thank you, Sunny. Okay, I'm going to go the opposite direction and ask a low-level question for Mehdi. So Mehdi, we hear a lot about HVDC, high voltage direct current. Can you talk a little bit about what is the difference between HVDC and MVDC? Is it arbitrary? Is it based on a voltage level? Is there a difference in technology?
Yes, so for HVDC, anything above 100 kV, it is considered HVDC for power transmission. MVDC is mainly integrated into the distribution grid, and HVDC is basically for higher power transmission, and it is basically in transmission grid. So as far as the topology and the control, they could be the same, but the HVDC, there are higher power converter topologies used. They can be voltage source converter or they can be line commuted converter. Uh, and the same topology actually can be used for MVDC, but MVDC then, since actually that's a lower power, their building block or power module is smaller, so basically mainly that's the voltage defining the MVDC and the application that they are distinct between MVDC and HVDC.
Thank you. Can you maybe talk a little bit about, so you mentioned line commutated converters. And so can you talk a little bit about these massive systems like in China or elsewhere that we're talking about, and how the technology that we would propose for these MVDC interties is drastically different from that? You mentioned line commutated converters versus voltage source converters. Not everybody may know the difference.
Right. So as a voltage source converter, that basically the control is on the voltage. So we are controlling the voltage. So basically, we are generating some voltage and we are controlling that voltage. So line commuted converter, mainly that's like a current source. So they are controlling the current. So it's basically based on the control and the topology. So they need to have higher inductance there to control the current. And for higher power, normally that they use a line commuted converter. So for lower power, mainly actually that's a voltage source converter.
Okay, thank you. And a question for Darren. You mentioned something about possibly directly connecting wind turbines to the DC intertie. Can you talk more about that, and maybe also indicate whether you could do this with solar as well?
Yeah, and I know Meaty touched on that in his presentation a little bit, as far as connecting DC resources together on a main bus to take advantage of the DC line. Basically, the power conversion on an AC, you could forego that by not having a transformer with no load and load losses, so it'd be more efficient. I know there'd be some challenges, but then you're directly feeding right into the DC. It's a conceptual design at this point, but I think I know in the larger installations on wind farms out in the ocean, they're looking at connecting higher voltage DC, similar to what we would apply on the lower voltage, medium voltage DC, to take advantage of the distance out in the ocean. So it'd be a similar concept, but applicable more on the DC side. And then there's a cost component as well. If these converters work and prove themselves out, then I'd imagine over time the cost would go down, and then there's be a certain point where the cost would be favorable to do that on the DC versus AC. And then controllability as well. as Bill touched on in MEDI, to control it DC versus the AC and the complications and challenges on the AC side versus DC, since there's no frequency component. I also want to go back a little bit. I noticed the one slide I was missing. I think the only thing I didn't cover is this line will also implement a fiber design, fiber optics to be included, which MEDI said, we'll know that way we'll know the sending and the receiving voltage on the DC side, which would be critical, I think, especially if we extend the distance to 25 miles or plus, and even on the Kobuk one, to know what the voltage is at the receiving end, since we don't have, there's no communications there now to know what that would be. So that's a part that I missed in the presentation. So.
Well, I'm glad you brought that up, because I think this is a big topic. Sunny mentioned this ability to leverage efforts and lay communication as well as power. So one big question that comes up is if we're doing cable-based intertie for power, should we embed the fiber in the cable, or should we lay it side by side? What are all the considerations related to this? And I think this is for the large group, but let's start with Bill Thompson.
I think you have to be clear on what type of installation you're going to be doing with the cable. I mean, we've got three possibilities here. And one is simply traditional trenching, and you lay it in a trench. That means that you've got competent ground, basically, that's not frozen and also isn't expected to be a permafrost installation. And then there's the next case is that you're putting into marsh, which is not moving water, but it's very waterlogged, and you're anticipating that the cable is heavier than saturated ground and will sink down after it's been laid. And then the final one is actually river or lake installations, where you're actually putting the cable into the bottom of running water or deep water. I think in the case of trenching, there's no real advantage with having the fiber installed inside the cable, because you can lay the two cables side by side, or the appropriate amount apart, and then you can service each one. If you have a break in a cable, you can service it separately, and bring them both up in junction boxes where you have to do terminations or not, and treat them independently. With the other installations, there might be some advantage if you're dropping it across a lake, that not to have to do it twice, but just drop one submarine cable that happens to contain the fiber. I could see some reasons for that.
We have a comment from somebody in the audience who indicates that a fiber should be side by side. If you have any input on that, audience member, you can put it in the chat. I think it will be really helpful for everybody. Is there anybody else on the panel who wants to address this topic?
Just a thought on the overhead portion. I know we've considered running an optical ground wire with the fiber embedded inside the cable. So there's basically a stainless steel core with aluminum around it. It's typically what's used in transmission for shield wire at all different transmission voltages. But with these smaller loads and not a lot of current, a possibility would be to run that grounded neutral with the fiber in it, and utilize that in a DC eventually, where you just have two conductors, one a phase and the other one the other phase, and then that way on installation, you'd only have to put up one wire versus a fiber and a grounded neutral. Just a thought. There's some challenges with that because, but anyways, that's what we're considering, I guess.
Okay, we have, oh, sorry.
I was just going to say that the vertical height in a pole is actually pretty premium, expensive real estate, and it tends to be subdivided. We share our poles with other utilities, and so used to be in the old days, you have a certain segment that was for cable, another segment that was for telephone. Various utilities would have different segments vertically on the pole. When we realized that we could put dielectric fiber in and put it up with our neutral and not have to take up any vertical real estate for installing communications, that opened up some opportunities, whether we take advantage of that or not.
Yeah, so the experience from the audience is a person who ran miles of line in the past. Once you have the logistics to run one, you can do both at a lower cost, which we've actually also noted ourselves, and that splices will be an issue. Splices are expensive. And then, if you were going to repair one versus the other, it'd be much easier if they were separate. Continuing along that thread of, actually laying cable, Bill, you want to talk a little bit about the amphibious equipment that you showed there in your slide?
We did have, there was a project in Manitoba that we leaned on heavily when we were trying to come up with methodologies and equipment to install cable over marsh areas at a low cost. This is this middle case where you're installing on land. You could do it in winter when it's frozen. The expectation is that when this ground thaws, that the cable, especially an armored cable with steel, would sink into the ground and disappear from sight. So the idea is to do it in the winter, do it at very high speed. Yes, the cost of the cable is higher, but the cost of installation is much lower. And so that's my holy grail. What I hope would end up being a much lower cost for interconnecting our villages together using MVDC cables and armored cable that's stretched out. And for that, what you need is as big a reel of cable as possible. Now, this is an inch and a half or 2 inch. Once you put the armor on it, it's not small cable like a fiber cable. It's going to be fairly skookum, and you do have to have it on a large reel. So you do need something that you can pull along in the winter, some kind of sled that can unreel this cable and then drop it without hoops, without just as a straight line on the ground, and then have it reasonably protected until it can melt into the ground in the next spring. So the equipment, I don't even know if the equipment has to be specialized, except that it's got to be a skid that can be skidded across the ground. You've got to have some kind of tug to pull it along, and then you have to have a mechanism for unreeling the cable. And all this stuff's being invented many times in the past. There's places around the world that this has been done. The installation in Manitoba that we were looking at was for fiber, and they went hundreds of miles with fiber in the sort of same terrain that we've got here. And they did use a plow to trench it in, and they did it with either with a boat or with large rubber balloon tired vehicles. And it's good to look at that. We have a very a variety of terrains that we have to put. If we put a cable between villages, we're going to have all three situations where we're dropping it in water, we're running it through marsh, and we've got it on competent ground, and we're going to have a method that covers all three.
So so Rob Benson has posted a link in the chat to this particular amphibious equipment. I believe it was 900 miles of fiber that they deployed across Canada. And the installation was done in the summer with these large balloon tires that Bill is talking about, which would not damage the tundra. So there's a pretty cool video if people want to check that out. So continuing along this line of, cable routing and layout, on Ask Sunny a question. Sunny, from a landowner perspective, what should planners consider when identifying routes for an intertie between remote communities?
Well, if you can, I think it's important to use existing easements. But also I would, take in that traditional knowledge and, make sure that it doesn't impact subsistence or traditional activities. I think outreach, education, providing information it's extremely important, but also staying off of native allotments, making sure that you work with the lands department, identifying where those are at, and work with the contractors and the consultants to make sure that you're not interfering with other people's property.
Thank you. Thank you. Okay, so now we have a question. I think I'm going to toss this to Darren. Can you clarify that the MVDC requires 3 conductors between inverters in the aerial configuration or just 2? Can you describe the aerial conductor requirements and pole top configuration design for the DC construction?
So specific to the Kobuk Shungnak line, there'll be 3 phase conductors and 1 neutral conductor. So that's conventional for 3-phase distribution. So phase-to-phase voltage would be 12.47 between phases and 7,200 volts phase to the grounded neutral. On the outer phases, where we'd run the 25 kV DC, there'll be 25 kV between the 2 phases, and then there'll be 12.5 kV between the phase and the grounded neutral. So back at the converter side, that's where, if you remember the layout, the topology of the converter design was 12.5 kV from the phase to the grounded point, to the center point, for each of the phases.
Was that actually necessary, or could you have run, maybe this is a question for Darren or Mehdi, could you just have run 2 poles, just a plus and a minus, and not have the center point?
I think that's, as far as the dielectric, I guess that's easier. So each cable to ground is 12.5. So it is cheaper for converter, and I guess cheaper for if that overhead. So the cable actually is cheaper as well, or overhead line is cheaper, because the dielectric is to ground is just 12.5. And for protection, if there is any line to ground, then we just detect the ground wire, the ground current. So as far as the protection is easier, but I guess it's very cheaper to do the lower dielectrics, lower voltage, 12.5 instead of 25 kV and 0.
Is that true for overhead as well also, or is it mostly just true for cable?
So that's maybe that's a question for Darren, I guess. But for the power converter, so if we do 0 and 25 kV, we need to have a little more dielectric. And for cable, my understanding is if we do the isolation, then you need to have isolation for 25 kV. Is that's one of them? One of the cable is 0, one of the wire is 0, the other one is 25. So you need to have much more expensive isolator. But if you do minus 12.5 and plus 12.5, the isolator should be cheaper. That's my understanding or perception, but I guess Darren can comment much more on that.
Yeah, on the overhead portion, to convert or re-insulate an existing 12 kV line to 25 kV, the insulators are relatively inexpensive. So as far as re-insulating to 25 kV, That's about a 5%, roughly about a 5% cost increase for the overhead. It's the underground that makes the big difference, and that's for the extra insulation that you need from 25 kV down to 12 kV. That BIL is significantly more, and it costs a lot more to have 25 kV cable versus 15 kV or 12.47 kV cable with 110 kV BIL insulation.
Darren, I'm not sure, I might have missed it. Were you able to address the second part of the question? Can you describe the aerial conductor requirements and pull top configuration design for the DC construction? I may have missed it because I don't understand the technical.
Oh, so it'd be typical RUS 25 kV standard construction for the AC, and it would also be applicable to the DC. So the insulators would be rated 25 kV DC. It doesn't hurt to have extra insulation anyway when you're running cross country, and it doesn't cost that much more, about 5% more just to go with the 25 kV rated insulators. Go ahead, Bill.
I may be causing some confusion here because when I did my slide deck, I was trying to compare the lowest cost URD cable, our standard 12.5 kV line construction. Number two, ACSR, basically the smallest stuff that we ever install, and see how it worked with AC and DC. And so I ended up with unipolar rather than bipolar designs at 10 kVA because I'm concerned about the cost of getting the voltage up on these PPSPs. So I figured, well, let's drop the voltage as low as possible and see how low I can go, basically, a little limbo here. And 10 kV worked, but it was linear. It was unipolar because I tried to do it with one single URD put between the villages to reduce the cost, and also doubled up on the conductors to reduce the resistance loss. Unipolar didn't matter because the neutral was at relatively low potential to ground anyway. So two different approaches. I'm concerned how much the cost of 25 kV PPSPs is going to be. That was what was driving me. So we have two different things going on here.
Okay, so I think we are at time. I really appreciate all of you all spending this hour and a half with us. We were lucky to have a little bit of extra time, so thank you all very much.
Yes, thank you all. I really appreciate all of the knowledge and expertise that you shared with us this morning. That was quite detailed and in depth, some of it a little bit over my head, but it is very fascinating, and I really appreciate what you shared this morning. So next, we're going to move to a moderated discussion on out-of-the-box ideas, macro and micro grid opportunities. I'm going to be joined by Peter Asmus, who's the Executive Director of the Alaska Microgrid Group. Please continue to drop those questions in the chat, and we'd love to integrate them into our conversation here. Peter, thank you so much for joining me this morning. How are you?
I'm doing pretty good.
Fantastic.
I'm not in Alaska. I'm actually in Bodega Bay, California, but like I tell people, I'm about as close to Alaska as you can get in California. I live in a fishing village, and I'm near the Russian River, which was where the Russians came through Alaska and occupied this part of California. It was sort of the boundary between the Mexico controlled part of California and the Russian controlled part. So I'm about as close to Alaska as you can get, and still being in California.
Well, it's interesting how geography connects us all and our history. So with that, do you mind introducing yourself a little bit more and telling us a little bit about the Alaska Microgrid Group and the work you're doing?
Sure. Well, I just added up how many years I've been doing energy-related stuff. So I was trained as a journalist, started out as a trade journalist, and I realized it's already up to like 38 years. I kept telling people it was 32, and I just added it up. I guess it's actually 38 years. So I came into the energy world sort of by accident, but I lived in a town, Sacramento, which was undergoing a lot of radical changes on energy policy, including being the only city to actually shut down a nuclear reactor by a citizen vote and then replace that with cogeneration, energy efficiency, and stuff. So I kind of started about energy literally in a municipal utility setting in my own backyard. Um, I've written several books, one about wind power, one about the history of California. Currently working on a book about the history of Alaska, energy innovation. I think maybe some of you saw the blog that I think it was posted yesterday. That is Phil White, who has one chapter in the book. I'm more kind of a managing editor for that book. But the reason I got connected to Alaska was through, of course, Gwen Holdman, who I headed up the microgrid research at a consulting firm that was originally called Pike Research, then Navigant Research, then Guidehouse Insights. And she said, I don't think you have enough Alaska projects in your database. And so she helped us build up the Alaska data, which lo and behold proved that Alaska had more microgrid capacity than any other US state. So I've been working here with ACEP and the Alaska Microgrid Group for just over 2 years. The Alaska Microgrid Group's a small consulting firm. The idea sort of being taking the knowledge from Alaskans and exporting some of that knowledge to other countries, but also doing work within Alaska. So last year we were hired by a company called Innovis, which has a variable speed generator, which enables integration of, well, makes it easier to integrate renewables into Alaska microgrids. So the project we did is we tried to identify sites where that technology might work. We now have a potential project in Kenya where we will be working with a company I've met who's based in Australia, developing some microgrids for very rural sort of areas. And we're hopefully going to do some work that we've been in negotiations for a while. And then right now, the Alaska Microgrid Group, we're finishing up a white paper where Clay Copland of Cordova is a co-author, looking at how to deploy edge data centers within Alaska's remote microgrids. The first installation is happening in Cordova, and it's pretty exciting to see the parallels between energy infrastructure and data infrastructure. And apparently the data center market is shifting from, I mean, there's still very large scale data centers being deployed, but those sites are being gobbled up. So the new trend, sort of just like microgrids, is having edge based systems, smaller modular systems. And that white paper should be done this month. And Clay Copland will be presenting that white paper at the World Energy Congress in Europe later this month. So that was a very long introduction.
No, that's exciting stuff.
Okay, there you go.
And quite the reach. And as we know, there's a lot of microgrids in Alaska, as you noted. And, our panel here is talking about, out of the box ideas, macro and microgrids. We know there's ideas on both. So kicking us off here on our conversation, and please, audience members, we would love to integrate your questions into our conversation here. So as they come into the chat, I'll be taking a look at them and weaving them into our conversation. So please continue to use that forum. So starting us off, Alaska has more microgrids than any other U.S. state, but unlike the rest of the U.S., most are isolated power systems deployed by utilities. In the lower 48, most microgrids are grid connected and deployed by non-utilities. What can the microgrid industry in the lower 48 learn from Alaska? And what can Alaska learn from the lower 48?
Yeah, well, I think first of all, that was I don't know if it was my biggest surprise, but I think it is a surprise for almost everyone I talk to here in the lower 48, is that utilities are in the driver's seat for microgrids in Alaska. And of course, that's out of necessity because those are the energy systems. The utility system, generally speaking, is a microgrid. And so I think what the lower 48 can learn is that, like here where I am in California, a lot of the microgrid advocates have been complaining for years about how large investor-owned utilities keep seeming to put obstacles in the way of microgrids. Now, a lot of that is just based on rules that started with a monopoly assumption of a sort of utility monopoly, which is gradually being chipped away at by deregulation and other changes. And so there's often this perception that utilities are the obstacles to microgrids here. Now that is starting to change. Utilities are deploying microgrids. In fact, the first major utility deployed microgrid was in California. It's down in San Diego area. It's called Borrego Springs, where this might be of interest after the last conversation. The utility, it was an R&D project, but it was more cost effective to just build a microgrid than to extend or actually reinforce a transmission line that went to a remote desert community. And that microgrid started out, maybe it was 3 megawatts, but grew to 33 megawatts when over time a big solar farm was integrated into it. So I think that's what we in California and other states can learn, that utilities are major innovators on microgrids. I mean, that's what my book is basically talking about. We're going to have a chapter on Kotzebue, a chapter in Cordova, chapter on Kodiak Island. We're going to have other chapters, but those are some in-depth case studies actually in the voice of people there. So Clay Copland is writing his own chapter. We have Darren Scott and we have Brad Reeve telling those stories. So I think, that's what folks down here can sort of learn, that yes, utilities can be innovative. And if you look globally, utilities, it varies quite a bit. I have a global perspective on microgrids. We used to have a global data set trying to track all the microgrids in the world, which basically was impossible, but we did our best effort. So I think that's what the lower 48, what Alaska can learn about. One thing I'm struck about Alaska infrastructure is a lot of it is funded by grants. And, some of that is because Alaska is a remote area. There's not necessarily a lot of private capital that has been going into these microgrids. So what the big trends in the rest of the US are, there's two I'd like to highlight. One is this idea called energy as a service. So this was sort of started with the company Schneider Electric, where they built a microgrid for a local government in Maryland. That local government didn't have the capital costs to pay for the microgrid. So this new business model is that actually a subsidiary of Duke Energy, super large utility, invested in the microgrid. Schneider Electric basically built the microgrid and then had a contract with the local government guaranteeing a price, guaranteeing carbon reduction emissions, making a bunch of guarantees. So the local government didn't own the microgrid, but it basically received the benefits without having to invest any money. So that's kind of a trend. There's several other vendors out there that have some variation of that. I think it's particularly attractive to local government critical facilities. Like I've been advocating for it here in California. We have a lot of small water districts, fire districts in rural areas. We've had a lot of power outages from wildfires. I think that's one way to get more microgrids deployed, because a lot of these agencies, they're often run by volunteer boards. They don't have a lot of capital. The other big trend is towards modular microgrids. And I don't think that's a great fit necessarily for Alaska, but the idea is one of the challenges of microgrids is each microgrid is a customized. I mean, that was what was touted as a positive. That's a customized solution, exactly what you need. But what that means is that every project is custom engineered. That takes a lot of time. So now there are vendors who have like microgrid in a box, you could say, where they say, here's a microgrid that's a 0.5 megawatt, but they will come with, like there's one company called Scale Microgrid Solutions. It comes with, has to have solar, has to have batteries, and has to have a generator. Now that generator could be fuel flexible. I think that's the other trend. So over time, you could maybe switch from natural gas or diesel to biogas or whatever. So that's the other trend, is this idea of the microgrid is sort of pre-configured. And that makes most sense with commercial and industrial customers, maybe like Home Depots, which might have 50 stores in the US. They all may be of similar size. And so that, that might be a good fit. So that's what some of those, energy as a service in Alaska, I'd be interested. I'm not sure if that would really work, but those are two trends. I think, Alaska just think more about financial innovation, especially as maybe some of these microgrids might grow a little bit in the future, or there might be microgrids within microgrids.
Well, especially that energy as a service kind of seems similar to the conversation we had yesterday. We had Mr. Mike Kraft join us from an IPP perspective. And I also referenced there was a quote at our last workshop where one of the utility CEOs mentioned that he didn't necessarily see utilities moving forward with creating their own generation, that they anticipate seeing more IPPs generating the power and doing that. So not exactly what you're explaining there with energy as a service, but I think we're taking an aspect and moving forward with that. So it'll be interesting to see that develop. Interesting concepts, and that modular thing. I can understand the concerns, but that could also, like you mentioned, have various interesting industrial and commercial applications. So thank you for sharing those.
Yeah, and the IPP. So one thing I have learned about Alaska in this book, of course, is the PCE program and some of the subsidies and why IPPs. One of the chapters in this new book is with Ed Byfeld, who is basically an independent company developing solar projects for utilities in a way to not lose the benefits of some of the subsidy programs out there, which are well intentioned and have worked well, but in some ways can conflict with certain aspects of trying to add more renewable generation. So I think IPPs seem to be playing a bigger role in Alaska, and I think that's a trend. Energy as a service could piggyback on that. There are sort of IPPs that do similar kind of projects, so it could definitely have an impact in the future, I think.
So you did mention that a lot of Alaska's system is leveraging grant opportunities in order to build out our energy infrastructure. And along that line, there's a new DOE program with funds to support transmission infrastructure in order to help decarbonize microgrids by sharing clean energy. In Alaska, however, transmission connected microgrids in the rail belt, as Steve Colt once said, who we heard from yesterday, and I believe he's on today, is where the carbon is. What, in your view, is more important, new transmission infrastructure or public policy reforms enabling sharing of resources in existing transmission networks?
Well, this is where, and Steve and I have a little community radio show, and Steve came on. Oh gosh, I think it was last year, might even have been longer than that, where we talked a little bit about the decarbonization scenarios for the rail belt grid. I do believe, we're going to probably need both, but I haven't been officially advocating, but I think one thing I was struck by when I look at the rail belt system is I think the need for public policy reforms. I know folks like Chris Rose have been working on this for years, and I know there's been some incremental progress, but what I think is needed is, I would say policy reforms. I think that's something I'm more knowledgeable about. I have to admit, Brittany, listening to the previous discussion, I didn't quite understand all of it myself. I'm not an engineer, although I got a lot of it, and I have studied DC and all that kind of stuff. But I think what we need are more dynamic rates. So the pricing reflecting, when there's surplus, when there's shortages, actually things like demand response, which is basically the use of shifting of loads to integrate renewables. I mean, everyone talks about energy storage typically, and definitely energy storage plays a key role, and there's various types of energy storage. It's not just batteries, but I think things like dynamic pricing, demand response. I don't know. There's the other models having some sort of ISO, independent system operator transmission. In Europe and Australia, they even have a DSO, a distribution system operator. So that's even another, even more regulatory step to kind of allow almost a traffic cop both on the transmission system and the distribution system. Of course, the big issue in the lower 48 is this FERC Order 222. Wait, there's four twos, 2222 or whatever, which is supposed to enable resources as small as 100 kilowatts at the distribution level to sell up into a wholesale market, into a transmission system. And I know that policy has not been implemented as rapidly as some folks would like. And of course, the other aspect of all this with the railroad grid is EV charging, electric vehicles. There's a lot of hype about electric vehicles, but utilities have always traditionally viewed them as a challenge because each electric vehicle is the equivalent of a house. So if you have all these EVs coming onto the distribution system, that's going to create problems, that's true. But those EVs can also be a grid resource. You can modulate the charging of those EVs according to pricing or congestion on the grid. You can even use the batteries in those EVs as storage. There was a bill introduced last year in California that would mandate all new EVs sold in California be bidirectional, which would mean that they could send power back to the grid. It did not pass. It was turned into a 2-year bill, but it is still alive. That's kind of the outside, when we're talking about outside the box thinking. Think about the linkage of the transportation system to the electricity grid and being able to transform those EVs instead of a grid problem into a potential solution. So to summarize, I think policy reforms are important. I think actual transmission infrastructure is also important. But I think, a lot of the remote microgrids in Alaska are so far apart, certain times it's not going to make sense to build a long transmission line over sensitive habitats in some cases. In some cases, it will make sense. So it'll probably be a case-by-case decision on what makes sense.
Yeah, absolutely. And that's how a lot of our infrastructure is now, is really taking that case by case look at what the needs are. We do have 2 comments in the chat here. One of them making a note that most IPPs will be tribal. And then Steve actually chimed in and talked about managed charging. I also heard the term time of use rates being discussed. So I know some of those ideas are being considered and at least talked about. So it'll be interesting to see how they developed moving into our future. We only have about 3 minutes here before we have to go to the break. So I'm going to skip along. Wow, this went super fast.
I'm talking too much. Sorry. I thought we had a lot of time.
You're perfect. So anyways, I know. I thought we were too, so it just goes really quickly. To move the needle, what's more important, large-scale projects such as hydrogen export or innovation at the micro level, such as tidal turbines in, I'm not going to be able to pronounce that correctly. Can you pronounce it? Yes.
I think that's how you pronounce it. I had a hard time too. Well, I'm going to cheat on I know I came up with that question. I'm going to say we need both. I think one thing I've learned after studying energy policy and history is that nothing goes according to plan. Basically, there's always surprises. One quick example, deregulation in California. No one thought prices would ever go up, and it led to the bankruptcy of my host utility. I think you have to try a little bit of everything. I do think Alaska has such a rich history with the fossil fuel industry that, big companies like that are going to have to play a role. And if you look around the world, companies like Total, BP, Shell, they are now leaders on renewable energy storage, and a bunch of things. So I think you're going to need that. But I was so inspired by the story of Igiagi, a utility with 68 people. I mean, when you say this to other people, they can't believe utilities can be that small. Doing tidal turbines, putting these tidal turbines in the stream where the salmon flow, which has been their livelihood, and kind of, I don't know if you want to say take that risk or go out on a limb and just try that and actually work with the local tribes, the developer. I have their hat here, Ocean, it's ORPC or something like that. I'm sorry, I forgot the acronym. Work with the tribe about how best to deploy that with the seasonality of the fish and everything. So I think we're going to need both. I mean, my work lately has been more on the called distributed energy resources. So that's really where I've spent my time. But I think we're going to need both in order to get where we need to go.
Well, thank you so much for the conversation today, Peter. It's time for us to move into break. I really appreciated the conversation talking about opportunities with macro and microgrids. Please join us again after our short break here, and we'll talk about transmission planning. See you shortly. Oh, that break went quick. Thank you so much for joining us again. We are moving on to our next panel. We are pleased to be joined today by Mr. David Burlingham, who is the president of Electric Power Systems, and he's going to be talking to us a bit about current Railbelt hot topics, transmission planning. As a reminder, please submit your questions in the chat box, and we will address them in the Q&A immediately following this presentation. David, thank you so much for your time today. Could you please take a quick moment to introduce yourself, Electric Power Systems, and go into your presentation? Thank you.
Okay. Yeah, I work for Electric Power Systems. It's a company that we founded about 30 years ago. We're based in Anchorage. We have offices in Anchorage, Palmer, Wasilla, Juneau, Redmond, and Vancouver, Washington. And we do a lot of transmission planning. That's really kind of where we got our start. We did the 2017 Railbelt Transmission Plan, and we have done analysis of, I would say, a lot of railbelt transmission problems and a lot of studies to interconnect renewables. And so I'm gonna talk about the differences between the system as it exists today versus what the system is that we need if we're going to go to a renewable-based system. So in the existing railbelt transmission system, the railbelt system was historically planned to operate as a synchronous machine system. So that means that it was really planned around gas turbines or thermal generation in each of the three areas in Fairbanks, in Anchorage, in the Valley, and in the southern system in Homer. So it's based on the fact that you have that synchronous generation in all three areas and that you have minimal transmission connections between those. Yeah, so it does not consider any investor decisions on capacity planning. So for instance, it doesn't consider the fact that if this were a private grid or a privately developed generation system, that you would be concerned that your generation may not be used all the time, because if the tie line's in service, you wouldn't use your generation, or you might if you're selling to another area. But if the tie line's out of service, then your generation would only be able to load in your area. And so, just so everybody understands, the transmission system does have periodic outages, which have lasted a long time. Last couple of years ago, we had the line between Anchorage and Kenai was out for about 3 months because of a fire. We've had the intertie to Fairbanks be out for, a couple of weeks. I don't think it's ever been out for a long period of time. But as the intertie ages and as the existing Kenai intertie gets rebuilt, it will be out of service for periods of times, up to 60 days each year, which has a tremendous impact on the generation and the operation of the system. The other thing that the existing system does is, because the transmission it's a transmission deficient system, so there's not a lot of interconnection possibilities for renewable operations. There's only a few transmission lines that can support renewable operations or connections at the current time. And in addition to that, for every 60 megawatts of generation, which is the 60 megawatts is the largest generation resource that is allowed on the rail belt at this time. And for every 60 megawatts, your 230 kV transmission line costs about $1 million a mile, and you have about $30 million for the interconnection substations on each end. So, like I said, Alaska is a transmission deficient system. So there's not a lot of transmission capacity out there. There's very little substation capacity. So any more connections of renewables really does have a barrier to market. And it is a barrier. It is a barrier to transition. It is a barrier to transition to different generation characteristics. So the rail belt was designed with one characteristic in mind, and that is synchronous generation. So changing to asynchronous generation or IBR generation, it takes some design characteristics which were not considered in the existing rail belt design. And the limited geographic diversity opportunities for renewables, because the transmission is geographically limited, right? We don't have our transmission system, the rail belt transition system is roughly 700 miles long by about 20 miles wide. So when you're talking about a lot of different diversities and a lot of different applications for renewables, at $1 million a mile, it takes a lot to get from a renewable thing to a transmission line in Alaska. So this is a map of the existing rail belt system today. So for those of you that aren't familiar with it, these lines in kind of a blue, this is the Kenai system. The Kenai system, roughly from here down is Homer. This system is Chugach's. This system is MEA's. This is AEA's, and this is Golden Valley's up here. So in the existing system, all of this transmission down here is already fully allocated for capacity. So even though there's a lot of wind resources down in this area, there's no way to get it to any loads. So you cannot bring it up. You can't bring it up either of these two lines. Bradley uses all of these lines. And in addition to that, this particular line is a 4-aught line. And for those of you that don't know, that's a really small line. It's capable around 60 something megawatts, 65 or 70 megawatts. So even though there's a lot of lines on paper, there's very few lines that you can actually use. In the south central area, the biggest thing that you can use are the 230 kV lines from Beluga into Point McKenzie. These lines right here can support, quite a bit of renewables. So that is one particular area. This line here that goes up the arm right now, this is a transmission limited line. It can only carry 75 megawatts right now. And it would require a major upgrade and also other improvements to carry more. This line right here, which goes around Kinnick Arm, around the flats, that is a ratty old line. And you cannot carry anything else on that other than what's there. This is the intertie. The intertie is fully allocated going north. It has some capacity going south, but it's fully allocated and it's a single line. This is the Golden Valley system. And even though on paper you look at it, you can put renewables in a lot of places. The only place you can put a renewables project that's greater than, say, 100 megawatts. I mean, we didn't run any particular studies to determine this, but the studies, we have run a lot of wind studies to determine where we can connect up in this area. From about on the old line coming down here, 20 or 30 miles, 40 miles out of Healy, down around, you can connect anywhere on the new line. And then once you get up into here, you can connect anywhere on the old line up to a point. But if you get very much, this line right here, which is about a $20 million improvement, needs to be connected to tie the loop from here to there. So you can see that the rail belt system is a really skinny and very weak transmission system. It's not conducive to development of renewables. So that's kind of where we are today, where all of these systems are really transmission constrained. So how do we get around that? What do we do different? So first of all, talk about in an islanded system, the characteristics of the generation resource really influences the topology of the transmission system. So if we were going to plan a new system based around a synchronous generation, let's say that we had mini nukes or hydros, and then we had some amount of wind, like 300 or 400 megawatts of wind, then that system would look completely different than a transmission system that was based on 100% wind or 100% IBR, more correctly. So that what you want to do is you want the new transmission system to allow a broad range of generation types without having to have a lot of transmission improvements. If you want to use different types of generation anywhere in the system, you want it to be as flexible as you can. The other thing you want to do is the new transmission system must expand the geographic diversity of renewables. So you need to, instead of having a 700-mile footprint that's 20 miles wide, you want to have a 700-mile footprint that's maybe 60 or 100 miles wide. And the new transmission system must allow development of renewables that are currently not economic. By that I mean there are potential hydro resources that are currently not in reach of the rail belt transmission system, which in a new system, they may be economic, they may be in reach. You may be able to get to those. And then we've got to lower the barrier to entry for any type of generation. So that's kind of the goals of the new transmission system. That's what we want to accomplish. So how does that end up? Well, if it ends up, this is the proposed new transmission system. So basically, you put in a second line between Healy and Beluga, and that doubles, that allows all of this area here to be integrated into renewables, and it allows possible hydro resources over in this area, which currently are out of the range of development, to be included. It includes all of this area, all of this area. I don't know if there's any resources down along the arm, but there could be tidal resources, for instance, that could be included now. And more importantly, it opens up all of this area. So all of this area could then have renewables on it and export that power to South Central and Northern Alaska. So what that takes is these two lines here need to be upgraded to 230 kV. This system here needs to be upgraded to 230 kV. And a lot of this system is being upgraded to 230 kV now by the utilities. But the things that have not started yet are none of the substations have been upgraded to 230 kV. So the line has, but the ability to operate at 230 kV is not there yet. This is a new HVDC cable link from the Homer system across to the Chugach system at Beluga, the old power plant. And what that does is it's DC to prevent stability problems between the Kenai and Anchorage. And this will increase the export capability between the Kenai and Anchorage to somewhere over 250 megawatts. From there, there's an HVDC line and possibly an AC line that goes from here to Healy that'll parallel this line between this point on the existing intertie to Healy. This Healy line would be upgraded to 230 kV. This old 115 kV line which is MEA's line, that's part of the northern intertie, would be upgraded to 230 kV. And then on the northern system, when you hit Healy, this existing line that Golden Valley built, this is called the northern intertie. That northern intertie is built at 230 kV. The substations along it are built at 230 kV, but it's energized at 138 kV, primarily because this line here is a really old 138 kV line. And if you carried all the power on the 230 kV line and then you lost it, this line goes out of step. So that's how come there's a limitation on how much power you can put on this line from a wind, how much renewable power that you can put in there. And so that's all of these projects are what are called the GRIP projects, Grid Renewable Infrastructure Program. And so all of these projects are what's called the GRIP funding. This is part of this line right here is the line that the state was awarded $206 million if they get a matching fund from the legislature to build this HVDC line. So this will be a really key line, really important. And then right now, I think that the Rail Belt is putting in some additional grant requests to further these upgrades. So that's kind of at least my vision or my hope for the future is to how you unlock the transmission system to allow renewables to be put in, essentially anywhere that you can find them, within reason of the rail belt, and not lock yourself into any single technology. I mean, we don't know what technologies are going to be available in 15 or 20 years. I mean, who would have thought 15 or 20 years ago we would be where we are with IVR technology? So this transmission system allows development of renewables, but it also allows development of synchronous type machines, hydro machines, and machines that we don't really know about yet. So the rail belt system is severely constrained. The existing system is severely constrained. It's constrained by topology, the fact that it's only one line in most areas, and also its electrical characteristics. It has stability limitations throughout its length. It is not renewable friendly. I mean, it's just not. It wasn't built for that. It's not that it can't be modified to that, but if you want to go to, for instance, 100% IBR system, and just to make sure that we're speaking apples and apples, an 80% renewable system by energy is 100% IBR transmission system. So what that means is that although you're getting 80% of your energy over the course of the year from IBRs, during the transmission peaks, you're getting 100% of your renewable by peaks, by IBRs. And I think one thing to consider is I don't think, I certainly don't believe that at some point in time in the future, that's going to be possible. I think there's no reason why technology-wise they cannot design an IBR to mimic a synchronous machine. I mean, that's the goal. And if you look at the new standards being developed by NERC, that is the goal for IBR design and IBR standards. But we're not there yet. I mean, I think we're really close. But if you look at the NERC characteristics or the NERC disturbance reports, and if anybody wants to see them, I can pull them on up after this. You'll see all the disturbance reports that NERC has issued in the last several years due to the fact that the IBRs don't behave as designed. And, they've created quite a few grid disturbances. We talked about, or we didn't, but somebody talked about KIUC yesterday. KIUC is a 100% renewable system. They have about 80% IBR system on peak. We have been involved with KIUC for, I don't know, since 1997, I guess. We haven't, we've done all of their transmission studies for IBR implementation. We've done all of their disturbance analysis, not all, I mean, but we've done a lot of their disturbances analysis. So when they have a problem with the IBRs, we get to look at it and find out what the problem is and what it is and what they can do to fix it or what they can do to try and work around it. And KIEC has done an amazing job. I think they were kind of in a unique place. They had a couple of really young engineers that were really sharp. They had a board that stood behind them, and they are an islanded system, so they don't have to worry about what their neighbor thinks about what they do and how they impact their neighbor. And they've been very, very good. They have a very reliable system. They have problems in their system. There have been IBR issues which have blacked out their system, but they address those issues and they move on. So I don't think at any point in time, I don't think that at some point in time in the future, and that 100% IBR system is I think at some point in time in the future, an IBR system is going to be possible. But right now, in my mind, it's not. There is not an IBR system operating in the world today that I know of with significant transmission. Ireland, which is probably the highest next to Kauai, is 75%. There's a bunch of people around 75, 80%. And I think 80% is a pretty doable and a pretty realistic goal. And again, that's 80% by transmission, not 80% by energy. That's 80% by power. And I think that our goal in a transmission system should be to allow 100% IBR if that becomes available in the future. But I don't think our transmission system should preclude other sources of generation by design of its technology or its characteristics. And probably the biggest obstacle I see from where we are to where we need to be, let's say if where we are today versus going to 100% IBR is the transition. If you run through the cases of how you would transition from where we are today to where we want to be, there are a lot of issues that need to be resolved, which I think is going to dictate the final transmission configuration differently than if you just said, I'm going to end up at this endpoint without having to pass through all these others. I think the transition from the existing system to the new system is going to be a major constraint, and I think it's going to take a lot of planning and consideration, and it's take a few headaches. So that's really all I have. If anybody wants to see any other information on anything, just let me know.
Great. Thank you so much, David. I really appreciate the map as you highlighted the different systems and where the opportunities were. That's fantastic. And if you're okay to stay on a little bit longer, I think there's going to be a lot of similar questions come in for both you and Jim. So I think a combined Q&A at the end of Jim's presentation would be prudent if you're okay to stay on for a little bit longer. Would that be all right? Sure. Okay, great. Thank you so much. So with that, then, I'm actually going to pass the floor on to Mr. Jim Mendenhall. He is going to be presenting on current railbelt hot topics, GRIP. What is it and why do we need it? Jim works at AEA. And before you get started into your presentation, please take a moment to tell us a little bit more about yourself. Feel free to screen share any slides that you may have. And the floor is yours. Thank you so much for joining us, Jim.
Well, good morning. Happy to be here. As Brittany said, I'm over at AEA. I've been here less than a year. Lifelong Alaskan, worked in a lot of construction related projects. So first, let me tell you a little bit about AEA, in case you're not familiar, and what we do here. we're the state's energy office. We work on power cost equalization, which provides a subsidy for rural power. We do grants and loan program, energy planning, and we work closely with Dave and others. And in fact, they're working on a strategic plan for energy for the state right now. We have rural energy power systems where we do the bulk fuel upgrades. We have circuit riders that can go out to the communities and help with some of their maintenance issues, doing a diesel engine emission reduction program. And we do training and assistance. And then there's a group which I'm involved with, which is owned assets. And we have the Bradley Lake Hydro. We have the Alaska Intertie, which Dave mentioned, that runs between Willow and Healy, Alaska. We have a Soldotna and Quartz Creek, an area, part of the line that runs between the Kenai and Anchorage, and that was acquired by AEA after the Swan Lake fire. And then we're working on the GRIP program. And so, so just kind of some background. This is obviously the state. The rail belt, which is right in this area, is the area we're discussing. About 75% of the residents live in that area. Stretches from down near or up near Delta Junction, Fort Greely, down to Homer. So that's 700 miles. And there are 5 utilities that operate in that area. It's Golden Valley up in Fairbanks, Matanuska Electric in the Mat-Su area, Chugach, Seward Electric in Seward, and then Homer Electric does the Kenai. And these areas are interconnected, work together to energize the state. And they all, for example, use power from Bradley, and there's a sharing agreement. And during the recent cold snap, I think Golden Valley was sending some power south to the area just so we could cut our gas usage. So the GRIP program, Grid Resilience and Innovative Partnerships, that was a program that was developed last year. They have 3 different areas where they'll put the money out, 3 different projects. One is grid resilience by the utilities. There's some grants available so they can upgrade their lines. And that then there's a second topic, which is smart grids, which increase the flexibility, efficiency of how these power systems work. And then the topic 3, which AEA is involved in, is the grid innovation. And we kind of piggybacking on what Dave talked about, upgrading our transmission system in the state of Alaska, and specifically the rail belt. And so this project, the GRIP project, we call it GRIP 1 because it was the first round. And so the idea was they would be interregional innovation and investments to accelerate the introduction of clean energy generation, distributed green assets, and reduce transmission requirements. So, and then I just want to talk for a minute, and Dave kind of covered this in his, but why are the upgrades needed? First, transmission lines, just to talk about when we say transmission lines, they're usually move power in either direction along the lines. They're typically 69,000 kV or more. And, most of ours are in the 115, 138, and hopefully 230 soon. The towers are taller, they're wider, and distribution lines, those are the ones you might see along the road, wooden power poles, just move power out to the customers. And so, part of this depends as, the strategic plan, which AEA is working on, is the utilities need to determine how much power they're going to need to generate in the future, where that power is going to come from, and where it's needed. And the purpose of transmission lines is to move that power from the generation to where the customer. And we have to do that at an affordable cost. In the Cook Inlet, the rail belt, the gas supplies are in decline. We need other generation sources. I expect that'll be some more wells. Importing gas has been discussed as an alternative. Dixon diversion, which is an addition to the Bradley Lake Dam, will will add a fair amount of power. And then there's other wind, hydro, geothermal, and those projects are being investigated. And I have a list later to talk about that. Now, typically, if you were in the lower 48, you'd have redundancy requirements. So basically, if one line failed, there's a way to get another more power out. And on the map Dave showed, you saw two lines coming from down near Homer up to the Kenai. While they both are limited in transmission capacity, there is an alternate path if one is taken down. You know, in 2019 on the Swan Lake fire, that took out part of the line from the Kenai up around Portage, through Birdwood Bird into Anchorage, and that energy was cut off. So and I think this winter we also had a short interruption from the Bradley Power coming north. And this summer they're going to be upgrading some power lines between Bird and Bird. They'll have the power shut down for about 60 days while they upgrade that line. And there's no redundancy between Willow and Healy, so if that line goes down, we're out. So this first project we want to talk about is the GRIP Round 1 Rail-Based Innovation Resiliency Project, and that's the one that goes from the Kenai up to Beluga. It's on the map. It's the yellow dash line, and we show a lot of the other lines here. You know, currently there's been some rebuild in this area that's being done, but the power from Bradley comes up around this way and into the central area of the rail belt region. So this provides the other power. Dave talked about these lines right here, how they're already, you know, there's lots of capacity on that line to bring it into Anchorage. So in January of 2023, AEA, in cooperation with 5 utilities, submitted a concept paper to the Department of Energy under this GRIP program, and it was to install a subsea cable, which we highlighted here, and in addition, put an overhead DC cable from Beluga up to Healy. And there were also 2 battery electric storage systems that would be installed, one in the central region, Anchorage, and then one up in Fairbanks. Homer had previously installed a BESS, and battery electric storage system is BESS. And that cost was about $826 million. DOE reviewed that project and encouraged AEA and utilities to submit a full application, which we did. And then in October, they said, we've accepted and we want to move on. You're approved for negotiation, but we're only going to approve the subsea cable from Kenai to Beluga. And if there's sufficient funds, we can build the 2 BESSes. So this capacity for this line would be about 250 megawatts. So what's that cable look like? I know one of the earlier folks from AVEC were talking about subsea cable. This is a typical subsea cable. Got the conductor insulation, lead sheath. It's got armor, probably 6 to 8 inches in diameter. And so we would put one of those down in the inlet. It's DC, which I know that Mr. Abul Hassani talked quite a bit about the benefits of DC earlier, and he was talking about MVDC, lower voltage. This would be up in the 230 volt range for our HVDC cable. We have about 37 miles undersea. We have the connections that go in where it lands, probably be done by horizontal directional drilling. And then, of course, on the north end, we have to run over to the Beluga substation, put in converter stations, and a converter station on the south. And we're still looking at where that converter station would be down south, whether it's in East Lake or Saldaña, and we have to get power there. Short distances underwater, AC cables are fine, but for longer distances, the HVDC has significant advantages. Also part of the project, as I mentioned, if feasible, were the 2 BESS This photo is actually the storage system that Homer's put in. And they have lots of, they're basically a battery set. And they use those for standby. If the generator goes down, you can draw the power off of these. You don't have to keep one of your turbines running at low capacity, being immediately able to pick up the power so that you can have plenty of time to start up. If it takes 15 or 20 minutes to start up a turbine, these batteries will hold it. So you're not basically have a turbine idling away and burning up fuel. They can absorb surges. They can, help with some of the power oscillations, and they can do a lot of things. Fairbanks had installed a BESS over 20 years ago, and at the time, I think it was awarded the most powerful battery system in the world, and it provided 46 megawatts for 5 minutes. And this Homer BESS, I think it has the capacity of 94 megawatts for 1 hour, or 47 megawatts for 2 hours. So in 20 years, we've gone from 5 minutes to 2 hours worth of duration. The two new BESSes that on Fairbanks and Anchorage, they'll both probably be in the 45, 50 megawatt capacity range. This picture has a couple of topics. One is the schedule. By statute, we have to finish this project in 8 years. The construction, we had this laid out on the design bid build, where you take the time to design it, permit it, put it out for bid, then you build it. We are looking at alternate delivery methods where it would allow us to order some of the long lead items significantly. It could take 2 or 3 years to get the cable. If we have to line up a vessel and get it in the schedule, that could take a couple of years. So we need to be able to have a good idea of what we're going to build well before we need to build it, so we can put it in. And what we show here is a cable laying ship. It comes down, there's some kind of a trencher down here, a jet plow, cable goes in, it lays it in, and then probably at the landing sites where it comes ashore, we'll use directional drilling to drill out. And so that way we don't have problems to scour or anything at those ends. The next page this is just to show you how they put in some of this cable. This is a jet plow, and as you can see, it sits on the runner. It's towed by a vessel. This arm, it drops down, has high pressure pumps below it, and it basically jets a trench in. The cable comes in, lays along the back here, and then lays into the trench, and then the action of the ocean or the Cook Inlet out there covers it up. Now, we're not sure this is how it's going to be done. Obviously, anybody who's driven down the Seward Highway has seen those boulders out there, the size of cars, and this will not do well in that situation. So, they've tried vibratory plows, and they self-destructed when they hit some of those rocks. So we still have to work on that, but our intention is to bury it. And of course, we have to. There's a couple of fiber optic cables out there. There's some pipelines for the inlet, so all that has to be considered. As this said, it's a unique opportunity. The HVDC cables, any power generation cable is expensive. As I think Dave said, it's $1 million a mile for 60 watts or 60 megawatts. And so, these cables could be, for some of the overland cable, it could be $2 to $3 million a mile for a subsea cable. So, being able to get the Department of Energy to have taxpayer money support this is very beneficial to the local residents. So what we expect is, DC is more efficient. There'll be less line loss, and so that helps contribute, not say throwing as much energy away, the heat and everything for the line losses. And I think typically, one of the guys said, typical overhead cable on transmission, they figure it's about 6%. We have this will add the redundancy around for another path from the Kenai up to Anchorage, and it will also, this helps create better stability. There's a lot of oscillations and surges on the system, and we think between the cable and the vessels that'll help with quite a few of those problems. And then there's also talk about a electrician transmission operator to kind of help coordinate the whole overall structure of all the different lines, whether they're owned or not. You know, on the slide that Dave showed, Golden Valley owns some up north, Matt Newsco owns some, AEA owns some, Homer owns some, Chugach owns some, and they're so in addition to all this, there's been talk about having a common operator for those. You know, this program won't just affect people on the rail belt through the power cost equalization. There's some subsidies that are given for rural power electrical rates, and those are based on what we pay in the rail belt. And so if we can help hold down or stabilize costs here, that helps out rural Alaska too. We talked, you know, the BESS, grid resilience, and reducing outage risk, and then new renewable energy sources. How do we get those connected into the grid? And later on, I have a slide about some of the projects that have been discussed. So it's all, so a lot of it in the stability. Slide is, so our project, 413 million, the Fed's DOE has appropriated 206.5. They're looking for a match of 15%, 50%. So the state has been looking at how they do that. We have some Bradley funds that are available. The state has appropriated some more money. And then they're looking at the long term. Are these going to be annual appropriations? Some kind of general from the general fund, or will it be revenue bonds? Nobody's quite sure. And one of the things we've talked to the feds about is we currently have $30 million in hand, which, you know, leveraging that with federal money is about $60 million, which helps, you know, which will easily do all the engineering and permitting work. And so we are looking, working with DOE to take an initial award and then have an unnegotiated portion of it, which will be negotiated in their match. They will release more money as the state puts in more money. So we're close to how we will fund this job, this project. The other project we put in for is, you know, the DOE released a round 2 of the GRIP funding for the grid resilience program. And as I mentioned, our original paper had a DC overhead line from Beluga up to Ely, and that was excluded from the program. So in January, we submitted a concept paper to include just this line, and DOE reviewed it, and then they went ahead and said they encouraged us to submit a full application. So we submit that in about 2 weeks, and this will be a redundant line from the central region up north. It'd be probably have 200 megawatts capacity on the line, so it definitely would add some redundancy and alternate path. You know, some of the big wind projects, there's some big wind projects up in the Fairbanks, Healy area. There's another one at Lower Mount Susitna, which is not far away. So that would, through this line, we could also have lots of competitors in they call it transmission constraint. This would reduce some of that. It would give us a lot more capacity on those lines. Let's see, here are some of a little chart of some of the major projects that have been considered. I expect some of them will be built, some of them will be studied, some of them may never get off the drawing board. We put in some geothermal. Homer Electric is looking at a couple at Mount Spur, Mount Augustine. We've got some big solar projects we're looking at with the sun. There's a biomass being considered up at Healy. We've got these little drops or hydro, and we've got both conventional and run of the river. So so all these would have a, we're looking at, the state is looking at alternates. I notice we didn't have any nuclear here. I know there's been a lot of talk in general about nuclear, but hopefully we'll get one of those on there. So that kind of concludes what I had to say just about what we're doing. This is the AEA staff. And so I guess we want to open it up to questions for Dave and I. We'd be happy to take a stab at it.
Great. Thank you so much. I really appreciate the maps personally. And I love the one that you just shared with all the different projects that are being considered. That's really cool. I think those visuals are really helpful for people to truly understand the full spread and breadth of the thought and considerations that are happening. I'm actually going to pull a question that we got at the very end of our last panel, but I think it'll still apply here. We've been hearing a lot about the natural gas shortage, and we've been receiving questions all workshop regarding what are some opportunities to make sure that we're meeting that natural gas shortage. So the question that came in earlier is, we just heard a lot about the various transmission updates. So specifically, how could some of these updates be used to help circumvent the impending natural gas shortage?
You want me to take that first, Jim?
Sure.
Well, the natural gas shortage in a few years. I mean, right now that's a pretty short time frame. There are a couple of fairly large wind developer projects that happen to be in the areas that I indicated that the rail belt could support in the existing transmission system. So those, hopefully, if those move forward, that would take a big chunk of gas off. I think that the other thing is that the rail belt utilities are actively pursuing other things which are non-transmission related. I think in the session yesterday, they talked about gas storage, which I think is a really good way to go. The impediment to renewables on the rail belt is not just transmission. It's probably as much regulation as anything. Because right now, unlike the lower 48, if you build a renewable project, you can go out on the market and buy regulation. Well, you can buy regulation services. The rail belt doesn't, similar to the way its transmission system was set up to serve 3 separate islands. It's also was set up to serve synchronous dispatchable generation. So it doesn't have any systems which really regulate or that are good at regulating. And so in the next round of generation planning, that's going to be a big issue. I mean, the rail belt's going to have to provide regulating resources for these renewables. That's just, to me, that's as important as the transmission. You've got to be able to regulate these resources. So does that answer your question?
Yeah, I was going to give Jim a chance to respond too, if he had anything to add.
I think, there's 2 sides to that. For gas, I guess, feeds 2 things. It feeds the electrical and it feeds the space heating requirements. And a while ago, I was just curious. So I have a house, my wife and I live there, and we use about 6,000 kilowatts a year, 5,000 kilowatts a month. And, based on the equivalent gas, we're using 41,000 kilowatts a year to heat it. So, I think what we have to do is look at how do we, it's easier to use renewables to provide electricity than it is for space heating. So every bit of kilowatt we put in that helps us prolong our gas is a good deal. Dixon diversion, that's an expansion of the Bradley Lakes. We're not putting any more turbines there, but we'll have more water, so we'll be able to run the turbines more than we are right now. And I think in 2030 that provides what is it, a couple of percent of the gas shortage. So you look at how these renewables can help save the displaced gas used for electricity. The other thing is, I think there's probably not personally, I don't think there's enough on how do we save gas and not use it. Just turn the lights off and do some things. But it is a complex question, and I think they're going to drill some more gas wells. I heard, and we're going to look at storage because storage is good. When you have the extra, you put it in. This last year, there are 5 wells that extract gas, and I think 2 of them sanded in, and that was one of the reasons we could only pull out 100 MCF a day versus 150 MCF a day. So there's no easy answer to how we do that.
Yeah, and to David's point, at our last workshop, we actually spent quite a bit of time talking about what is innovation within a utility framework, and regulation was one of the core conversation points. So for those of you that are interested, you can visit the Alaska Sustainable Energy Conference website and review the last workshop. Our next question, and this was originally, David came in during your presentation, but Jim, please feel free to expand on it as well. Can you talk about the potential to connect a transmission line to Delta through Glen Allen? My apologies.
We actually did a project for the Denali Commission where we looked at connecting the rail belt to Golden Valley through Glen Allen and with a radial line out to Tok. So we have looked at that, and there's the line between Glen Allen and Delta. It has some really significant voltage control and kVAR requirements that make it an expensive line to build and operate. If you're just going to go a radial line to Glen Allen, it is a lot better to go straight from MEA into Glen Allen as opposed to come down from Delta. But there is a project out there that's actually part of the long range transmission to build what they call the road belt line between MEA, which is at line stop around Sutton, all the way up to Glen Allen and then over to Greeley to connect with the Golden Valley system.
Thank you. Jim, did you have anything to add to that question?
Not much. I will just say that it is a long way. There's a lot of, it's not the higher voltages for typical transmission line. There is an extension being done from Delta Junction down towards the Black Rapids Glacier training site, which the military has. The military had been running generators there, and they decided that they wanted to run it down. So hopefully in the next year or two, they'll have a connection there. So it might be incremental changes that put that in, but we don't see any money there to expand that to a full transmission line anytime soon.
Great, thank you. David, again, this question is directed at you. What % of energy would you say 80% IBR by power generally works out to? Approximately 50%, another amount?
That's really a question of economics. I mean, you can put in 80%, you can put in more IBR and just curtail them such that you're not providing 100% of the power. So you can, for 80%, if you wanted to run at 80% IBR, you could essentially make it 80% energy if you wanted. That's a dispatch and a control function based on your system. So, I think if you just mashed it the way it is, it'd probably be around the 60 or 65% mark. But you can make it 80 if you wanted. That's an issue for curtailment. and what the economics of that are.
Jim, anything to add?
No.
Okay. The next one, the acronym NERC was used a couple times. So I believe it was the North American Electric Reliability Council or Commission, recently released a white paper in 2023 on grid forming functional specifications on bulk power connected battery energy storage systems, in which they stress the importance of requiring GFM capability and commissioning. Will GFM capability be required for the best systems? Anyone want to take that one up?
Yeah.
All the BESs require grid forming inverters, but I'll point out that a grid forming inverter for vendor A is not the same as a grid forming inverter for vendor B. And that NERC white paper, there's kind of a difference between the NERC people that are trying to get out in front of the technology development and the NERC people that are operating under this technology. I mean, can I share my screen for just a minute?
Sure. You should still have capability to do that.
Okay, can you see this?
Yes.
So if you look at this slide here, all of these NERC disturbances here are NERC major system disturbance reports from IBRs. So one of the issues that's in here, and some of these NERC disturbance reports are very scathing. For instance, on the last one, on this one, it says because they've had these disturbance reports for several years and nothing has changed, they blast them for systemic performance issues, about having performance issues that have not changed and not gotten better, and list of lack of proactive industry action and standards updates. I mean, because of this, NERC has IEEE issued a new standard, IEEE 2800, which defines a lot of the characteristics that you need to have on IBRs and how the IBR is connected. And this year they're gonna supplement that standard with a new standard on how an IBR has to be tested. One of the big problems with IBRs, and it's not just IBRs, it's any new generation, like all the new gas generation is the exact same problems. When you do a small signal test to try and get a model to put in your system to plan, your small signal test does not test all the functions of the IBR the same way it doesn't test all the functions of a gas-fired generator anymore. So NERC is trying to develop testing methods that will require all these IBRs to be tested and modeled before they're connected to the system. And so, I think once that actually comes into play, you're going to see a lot better performance in terms of the grid and a lot more acceptance in terms of grid operators of IBRs at high penetration rates. So I think that's going to be really key this spring when they issue that testing standard. And this is just one here. This is an IBR grid forming inverter that went unstable during steady state at KIUC and blacked out the system. Here's another one, a grid forming inverter. This red is what the simulations show it should have done. When it went islanded, it should have picked up the islanded grid and stayed connected. It didn't, it went black. I mean, these are the kind of issues right now that the industry is working on. And I have no doubt that they're gonna solve them, right? I mean, they're gonna fix these. And I think that we should be working towards, say, let's start with an 80% target, and then let's see where the industry is and see if we can go higher.
Great, thank you so much. If you don't mind, stop sharing your screen. We got time for one question. We're actually at time, but I just want to close us out with one final question here. First, just a general comment. I really appreciate the timelines that have been shared. It's the first time some have seen this. Question directly to you, Jim. Has AEA started the NEPA process yet? And if not, when would AEA have enough data to get started?
No, we have not. We expect that we will get an award soon. We will start the preliminary design and engineering. You know, we have to have probably 30% design before we can go to NEPA. And then we expect that to take 2 to 3 years out there because we're working in the inlet. We have endangered species out there. So it'll be a long process.
Okay, on that note, we do need to keep moving along in our presentations. Thank you so much, gentlemen, for joining us today. That was a lot of information. Again, I really appreciate the visuals and showing us the project areas, the geographic spans we're working on, all the projects that are being considered. I think that was just absolutely fantastic. I'm excited that we're going to be closing out a conversation that's really highlighting the current Railbelt hot topics. We are now joined by Gwen Holdman, who's the Associate Vice Chancellor for Research, Innovation, and Industry Partnerships here at the University of Alaska Fairbanks. She's also the founding director of ACEP. And she's going to be joined by Andrew Jensen, who's the Policy Advisor for Communications Assistant, Office of Governor Mike Dunleavy. He's really been working with us on a lot of energy policy things, and just really excited to have you two. So from here on out, the floor is yours, and I'll come back when we're doing closing comments. So if you don't mind taking a moment to introduce yourselves, kind of the role, what you're working on, and then take it from there, we are very happy to have you here today. And for the audience, please continue using the chat to put your questions in. And I know Gwen and Andrew will be weaving those into their conversation. So with that, Gwen, the floor is yours. Thank you so much.
Thank you, Brittany. Can you guys hear me okay? Just want to double check.
Yep, we got you.
Okay, awesome. Well, thanks for making an introduction of myself and Andrew. I feel we've been really fortunate to sort of have you working with us in this space now for the last, I don't know, it's been about a couple of years since you really took on leading and developing the Alaska Sustainable Energy Conference with the governors. So I'd love to just pass it to you to give a little introduction for yourself and just kind of how did you get interested in this energy stuff? How did you get into this space?
Well, thank you, Gwen, and thank you, Brittany, and everybody at ACEP for putting these together for us. It's great awareness for the energy conference, and you're right. I mean, that was at least within the governor's office, where I've been since October 2021. I did get hired in as a communications assistant, responsible for writing duties, speeches, op-eds, those kind of things, and but the energy really goes back even further. I mean, I moved to Alaska in 2010 and spent the first 11 and a half years working at the Alaska Journal of Commerce. And so obviously, if you're covering business in Alaska, energy is, it touches every single thing. And so a lot of these things that we're talking about now that we're still working on, rail belt, transmission issues, RCA, those kind of things, certainly we were covering those things for the last, 10 years or so as those were discussed. And so, the energy conference is really how I ended up in the policy role on energy issues with the governor's office. Myself and John Espandola, who worked with the governor from the very day one of his term, we were tasked with putting that conference together at the governor's request in 2022, and did it for the first couple of years, 2022, 2023. And then, as some of you may know, John was appointed to the RCA last summer. And so when John was appointed to the RCA, it was a very short notice kind of thing. And obviously, there was a lot of work going on at the time, as always, with energy issues. And so it was sort of a natural fit based on all the work we had done with the energy conference to move into that role and try to make it as seamless as possible. And I thought the just planning for the conference, I think, really prepared me well for the role because it is a technology agnostic conference. And so it goes from oil and gas to advanced nuclear to hydrogen, carbon capture offsets, storage, all the things that we're talking about right now in terms of the state of Alaska and addressing our energy needs. So that's kind of how I got here today, and looking forward to the conversation.
Awesome. Thanks, Andrew. mean, I think this governor is a governor that clearly has a real passion for energy issues. We're at sort of a critical juncture in many ways in our state right now around some of these energy challenges that we have and really setting a direction for the future. And I know he's really personally interested and passionate about that. I'd love to hear a little bit more of like what you see as the priorities in the administration right now when it comes to energy. And then I'd love to chat a little bit about the task force and maybe what the next steps are related to the report that was an outcome of that work. So,
well, thanks. I mean, you know, the governor, as you know, is extremely passionate about energy and especially lowering costs. I mean, that is his main priority. Lowering costs for energy, lowering the cost for food, lowering the cost for childcare, housing, you know, across the board, which all goes back to when he first moved to Alaska. He moved out into rural and immediately noticed the price of gas and thinking, how is it that folks can make it out here? So, you know, he's very passionate about lowering costs, not just on the rail belt, but in rural Alaska as well. And, you know, he's not only passionate about that because, you know, energy costs are the foundation of economic growth. So you can't really have economic growth without bringing down energy costs. But he's a voracious reader. He's a technology, you know, kind of nerd. And so I'm always getting text messages from him all hours of the day about all kinds of subjects, whether it's, you know, new solar, you know, technology. I just got something from him about home sand batteries. I mean, he's fascinated by this stuff. He's always reading about it. And he sees just such tremendous potential for Alaska. You know, especially if you look at Cook Inlet, he can go on for, you know, unlimited amount of time about just the potential and the opportunity he sees. And so it's really important to him to harness these opportunities and to create an environment where all types of energy can be brought to bear, because as we all know, this isn't a one-size-fits-all state. What works one place won't work other places, but we do know as these technologies are being developed, what works in Alaska will probably work almost anywhere. And so he really does see Alaska as making it an attractive place for the deployment, testing, and development of these technologies, whether it's small modular reactors, or when you look at, you know, the interest in carbon capture and sequestration and the resources that Alaska has here, both in the biological abilities to sequester carbon and through our reservoir pore spaces and, you know, and saline aquifers as well.
So yeah, and then with regard to the task force, so that was one way that the governor was really interested in kind of organizing a bunch of skins from diverse backgrounds. I think that I don't know how many hours were put into that effort, but a pretty comprehensive report came out of that. What did the governor, what were his key takeaways on that? What was he excited about? What do you envision as next steps, either for that group or for sort of subsequent efforts that might come that task force effort might lead to?
Well, absolutely. As you mentioned, it was a very comprehensive report. I think there was something like 60 different recommendations within that. And so that report was delivered to us in the governor's office in December, which is, of course, right on the eve of the legislative session. And for those who, you know how the process works, drafting of legislation begins months in advance. And so what we did was we took a couple of key sort of takeaways from the report that we believed could really sort of be achievable in the near term as we continue to go through the recommendations and look for additional policy changes, regulatory changes, you know, budgetary needs that can be addressed over the coming, you know, months looking into next year as well. But certainly if you look at the legislation the governor has introduced this year, specific to things that were addressed within the task force report, are looking at the transmission system on the rail belt and replacing the current method for transmission cost recovery, which we know is wheeling, and then also looking at incentivizing or just maybe taking down barriers to independent power project developers by providing some equal tax treatment for them, and to sort of, again, like I mentioned, create the environment where the private sector can come in and address some of these needs. And so I think that when we look at, which was the major sort of new piece of legislation that was put forward this year, we believe these are some very tactical things that might seem sort of small, but we actually believe that are going to have a major impact in helping strengthen the transmission system and allowing multiple power generation types of any kind to come onto the grid and lower the costs for electricity on the rail belt.
Was some of the thinking in terms of pulling out those particular recommendations as like near-term areas for effort really around the sort of federal opportunities and how this policy sort of sets ourselves up here in Alaska to really take advantage of those?
Well, definitely. I mean, and the federal opportunities, and those, came to us in October. That was obviously great news. The governor's 100% committed to getting this project done. And so in the near term, that's why some of these things kind of foundationally have to be done while that project is designed and built, because that will be probably a 7 to 8 year process if it follows the track that the federal government has, what AEA just laid out in that project timeline, that we need to set up some policies to take advantage of that infrastructure when it is built. And that's one thing that AEA was already working on with the line that it owns down on the peninsula. Getting that project done is very crucial in the near term and won't take as long as the GRIP project, but that will go a long way towards unconstraining the system, freeing up more Bradley Lake power. That project alone will go a long way towards lowering costs for Alaskans by making more of the Bradley Lake power available. So you kind of had a nice convergence of things all at once, where we have alignment among the utilities, first of all, in even putting that application forward and agreeing on the needs, agreeing on using bond payments that are owed for these necessary transmission upgrades. And then also looking at the issue, yes, of the way we recover transmission costs, because we're not talking about really the ratepayers pay those costs no matter what, but we change the way we pay them. And I think that that's one way where the independent power producers will have an environment to serve the entire rail belt and not just have their decisions constrained by regional considerations. So I think we just had a lot of things all kind of coming together at once, where there is a tremendous amount of alignment around these issues that we can capitalize on right now.
I'm curious what the governor of the administration's position is, when we look at things like these large capital projects, and we just heard about the GRIP projects. In the past, there has been often state investment in those kinds of large projects. We are a small state. It can be difficult for consumers to bear 100% of the burden for building out these systems with such a small number of people.
Building up off of that, how is the state working to help fund some of these, or what are the approaches? A lot of these opportunities do require some match funding. So how are we taking advantage of some of these opportunities to support these communities with such a vast number of projects?
No, I appreciate that. And, as Jim mentioned, we have some looking at the funding that's been now proposed for the current or the upcoming fiscal year. We've identified approximately $32.7 million in existing state funds between state funds on the general side, the ADA dividend that is paid to the state, some reappropriations, and then some bond funding that AEA had previously secured. So between those pools, that's $32.7 million towards the $206 million match with again, so that generates again another $32.7 million on the federal side of things. And the way these work is that as you spend, they match. As you spend, they match. And so there's a tremendous opportunity over the next several years to fund that project. And there's multiple ways you can do that. There's different ways to bond for things. There's other ways to finance. And so we're exploring all those options. But like I mentioned, the governor is 100% behind this project, having it funded. But as you know, I mean, we are in a situation where there's lots of need and there are lots of competing funding areas within the state. And so all of that has to be balanced in how much we put into here in a single fiscal year and addressing things, like rural Alaska and the needs that they have there. And so where you see funds to go into the renewable energy fund that AEA administers, you see things like the governor's proposal for a green bank. That's a very important priority for him. We really want to see that get through the legislature this year, because you have to put in some ways for the state to help fund and finance these projects. And so we have to be creative about it because we don't have unlimited funds. I think we know the federal government has much wider ability to create money, I guess you could say. that the state does not have. And so all of these competing needs within the state have to be considered. But, 100% the governor is committed to getting this project done. But we do have to be mindful of competing needs around the state, especially as regards energy and in rural Alaska, and making sure that their needs, which, if we're looking at 20 cents on the rail belt and what the costs are in rural Alaska, we have to make sure that that we're putting those priorities in front as well.
So you just mentioned the Green Bank bill. I feel like that hasn't got quite as much airtime this year, but it's definitely still very much on the table. It's called the Alaska Independence Fund. Or what is the actual title of it? Do you remember?
You're going to put me on the spot now. I mean, certainly.
Sorry. Yeah.
It's a proposal. This would be put within the Alaska Housing Finance Corporation as a subsidiary of that. The bill you may be referring to is the Alaska Affordability Act, where the governor has identified 4 priorities that I talked about at the beginning in terms of food, energy, childcare, and housing, and to where entities that have corporate income tax liability to the state can actually reduce their corporate tax liability by making qualified expenditures that result in lower prices in those 4 areas, whether it's energy, food, childcare, or housing. So we're looking at multiple ways where we can incentivize some of these things because the state, cannot do everything on its own, and so we have to be able to where the state can be a partner with the private sector to help advance some of these priorities.
So with the Green Bank bill, just kind of going back to that for a second. And that would be something that would really benefit Alaskans all over the state. We're not just talking about the rail belt in this particular case. And so can you talk a little bit about how that program is envisioned to be used as like one of these tools that we have in the toolkit?
Mm-hmm. Sure. Well, one of these, federal receipt authority is necessary for some of these programs. And so one of the first steps is you have to set up the entity that can then receive the federal funds. And so that's a big piece of just setting up a structure that is necessary to work within some of these federal programs. And then that's also the ability where, the Alaska Housing Finance Corporation, they earn income each year. One of the ways they're using their income this year is to provide this first-time homebuyer down payment mortgage assistance. They had a tremendous performance last year, around $48 million in income they earned, where about half of that money is going into that mortgage assistance program. So again, that's where state funds can come in and then be repurposed to do federal match or to provide grants or other financing mechanisms to help bring these projects forward.
All right. And so, because we have been, this session is sort of geared toward the rail belt, I kind of want to switch focus there a little bit. So as we both know, transmission has been a pretty hot topic in this area. You already alluded to the governor picking 2 priorities from the task force, which includes eliminating wheeling, and then also looking at creating this parity with independent power producers, tax parity with cooperative utilities, which happen to be the utilities that are primarily serving the rail belt. Can you talk a little bit about where you perceive that legislation being, or like what your hope is in terms of how that moves forward this legislative session?
Well, I think one thing that we're certainly encouraged by is there's certainly every indication of widespread alignment on these 2 issues. The utilities are on board with a different cost recovery mechanism for transmission, because certainly we're not talking about taking money away or anything like that from them. We're just looking at a different way to recover the costs, because currently, and this ties into independent power producers, because the way the system is currently, those transmission costs become part of their cost of power when they're working with the utilities to come up with a power purchase agreement. And so by simply shifting that cost to the end user, it's no longer a part of the IPP's cost of power that they have to work with. So, because in the end, the ratepayers are paying that cost. It's just a simple matter of how that money is recovered. And we believe and so I think that if you're not talking about taking money away, right, from a utility, they're still going to receive their costs for O&M, for depreciation, their interest expenses, all the things that go into operating the system. Those costs are still going to be recovered. But what it will do is it will allow independent power contracts to reflect parity with cooperatively generated power, which does tie into the issue of tax parity, because currently the cooperatives, as nonprofits or a municipally owned utility, they do not pay local property taxes. They pay a excise tax to the state on kilowatt hours sold. So what our legislation would do is just simply extend that same treatment to the independent power producer. They are providing a public service. They are providing electricity that has to come in at a cost competitive way, and by giving them the same tax treatment with exempting them from local property taxes, we believe this will go a long way towards bringing more projects online. And again, it does expand where these projects can be sited when you take away these sort of artificial constraints on, which wheeling charges will I pay, which property tax, location, who am I going to have to negotiate on maybe a property tax exemption. By just creating a level playing field, that will allow the private sector to take advantage of that in our view. And that's certainly what we've been hearing from the project developers who have expressed their support for this legislation so far in the committee hearings that it's heard.
It's really interesting, how like these small amounts of money, like related, wheeling or these property taxes, they can really make or break some of these transactions with power purchase agreements with independent power producers. Whereas like then in the big scheme of things, it doesn't change things that much in terms of how the revenue requirement the revenue requirement stays the same. And so how you're kind of calculating how those are recovered slightly different isn't a huge change from what's happening today. But like for those individual projects, it can serve as a really significant barrier for just kind of executing those deals. So I think that those are both really important things that it would be nice to be able to try to get done this session. I know there's a lot of things going on and a lot of things happening in Juneau. So
yeah, I'm actually kind of on standby today. The reason I'm down in Juneau is we were to have a hearing on the governor's transmission bill in House Finance to have its first hearing there. And they are, as some are well aware, they are working through their operating budget amendments. And so we have received word that this bill may not get onto the agenda today, but I am on standby in case they need me. I don't have a flight until late this night. But I mean, you raise an important point about what we're talking about here in terms of the very marginal type costs we're talking about and how it does make or break a project. The overall transmission, I appreciate Steve on your team working out those numbers. You're looking at around $70 million in transmission costs. And that is out of a total revenue requirement of around $900 million for the rail belt utilities. So we're not talking about a tremendous amount of money. We're talking about fractions of the price per kilowatt hour. But if you've ever looked at a cost of power adjustment or any regulatory filing, those decimal points go out pretty far in terms of the way things are calculated and what certain surcharges are, those kind of things. So those really do matter. And so even though it sounds like a small change, it actually can have a great impact. And so that's one thing where we're helping to work with the legislators on this. They've, certainly we've gotten very good receptions, and people are interested to understand how it works. And we are optimistic that because there is alignment on this, and it is important to members in both committees. It's very important to the governor. It's important to people in the private sector and the utility sector. That again, this is a moment we have to take advantage of. So yes, we are optimistic that we can achieve these things this year, recognizing there are multiple policy and regulatory things that still have to be addressed. I believe, like as David had mentioned in the previous presentation, there are still things that need to be done, but you have to start with some certain foundational issues, and that's the way we look at these issues, these two particular things that we're trying to get done this year.
So yeah, it's interesting because I think, both with this legislation, several of the pieces that he has introduced this session and the upcoming Sustainable Energy Conference, I think one of the messages that the governor's trying to convey is really that Alaska is also sort of open for business, for new opportunities, right? And so much of that is tied to the cost of energy and the availability of affordable energy in the state. And so I'm sort of curious, there's a question here about carbon capture sequestration, right? This has been one area that's been identified as possibly like sort of an emerging area for Alaska. Do you want to talk a little bit about like what are some of those bigger ideas, not just in terms of energy projects, but about how we might be able to use energy produced here to really create new business opportunities for Alaskans across the state?
Sure. And, as some may know, last year, the governor introduced two pieces of legislation, one to allow the state to monetize its biological resources for carbon sequestration. So our forests, our coastline for mariculture, et cetera. We did get that through last year. And one of the really key pieces of that, and those regulations, that package is working its way through right now. And I think it's going to be finalized fairly soon in terms of how those leases and how the state can then work with the private sector to earn in on that. There was already several mariculture projects that are moving that were in the permitting stage with an idea of capturing carbon through kelp and offshore seaweed farms. So there are some projects in permitting right now in terms of like forest lands. That regulatory package is nearing completion, I believe. So there's great movement there. And one thing that was important to get into that bill, because the other bill he introduced was around using the geological sequestration. So depleted oil and gas reservoirs in Cook Inlet and on the North Slope was to get permission to pursue Class 6 primacy from the EPA. And what Class 6, this would be the wells that you would have to drill to sequester carbon. And so the state and the EPA has actually received some money to actually help states acquire this primacy. And one reason, and this bill was actually hopefully to be heard on the floor this week. I think it's gotten pushed a little bit, but it's HB 50, which would create the regulatory structure for the state to lease space in our reservoirs to private industry to sequester carbon. And it's very important for that to get over the finish line this year, because what the EPA has communicated to us is that, it's great you're pursuing primacy, but until there's a legislation and a bill that's in place, the Class 6 primacy process will stall out. And so we're really hopeful that this will get done, because that will, we believe, attract a lot of private sector investment. We're seeing it on the Gulf Coast, where we have oil and gas majors, and including some from overseas in Asia that are looking at those carbon capture projects. Louisiana, I believe, just got this Class 6 primacy in December and took a couple years. So if we get through that this year, we would hopefully be able to get that primacy done and get this regulatory process stood up to monetize these vast resources. I mean, Cook Inlet has been estimated around 50 gigatons. That is Japan's emissions for an entire year. And McKinsey and Company looked at the state broadly a year ago, and they looked at North Slope potential, and they also looked at saline aquifers and came up with a number around 200 gigatons, which is, tremendous. I think that's something similar to total annual global emissions. So this is, again, where the governor sees what Alaska has to offer and all the opportunity and excitement around some of these things. And that's one thing about the Energy Conference. We're going to have multiple panels around carbon capture, around the technology, between direct air capture. There's big differences between natural gas emissions versus coal emissions. And we really see a lot of opportunity here to export technology to the rest of the world and export the ability to even import CO2 in a liquid form and inject it into wells. So there's just so much moving in this space that the governor is very excited about. And, we definitely planned our agenda around the optimism that this bill is going to get over the finish line. So we're really, that is a huge priority for us to get that done this year.
So I'm curious, like you've been working a lot on the agenda for the conference. Like, what are you most excited about this year in terms of who we're bringing up as speakers or a panel? Like, what are you most excited to hear about?
Well, one thing I'm really excited about this year, we've worked with the Department of Energy, Arctic Energy Office, informally, for the first couple of conferences. And this year we've really formalized that partnership. And, Aaron and Anne-Marie with the Arctic Energy Office have been just great to work with. And they're really bringing all this expertise from around the national lab networks and DOE leadership into Alaska. So if folks look at the agenda, and we're still kind of populating the speakers that are on there, but if you go look at the speaker list, we've got tremendous folks from across the national labs, across DOE leadership. They're going to be, part of our day to to start the week. We have a pre-conference event with them where the governor is actually going to sit down with the premier of Alberta, Danielle Smith, during the lunch hour, which I think Alberta and Alaska have a lot in common. If you listen to their premier talk, she sounds a lot like our governor in terms of looking at carbon capture opportunities, exporting ammonia to Asia, looking at net zero obligations while still producing oil and natural gas, because that is absolutely a part of the conference. But the DOE partnership, I'm very excited about. I'm excited that we have Jeff Waxman, who is leading the project Pele. I appreciate your connection with him and making some of those introductions to get us an update on that. But we have a great Department of Defense panel that's planned where we expect to have the Assistant Secretaries of Army, Navy, Air Force, and the Department of Defense to talk about what they're doing with their base power and how they're trying to meet some of their reduced emissions goals, but with secure power available. And advanced nuclear is something they're really pursuing. As we know, there's the pilot project in Eielson. The Army is looking at a similar track. Dr. Waxman is going to be actually traveling up to Fort Greely when he comes up for the event. So the Army is pursuing these advanced nuclear opportunities. They're looking at Alaska. We're a perfect candidate for some of these things. Like I mentioned, we're going to have a lot on carbon capture. One thing I'm really excited about, there's one we can't announce yet because he hasn't filled out his speaker form yet, but we've received a handwritten letter saying he's coming. So I can't announce it yet, but we're excited about that for our Wednesday keynote. And I'm also really excited we're going to get the ambassador, our ambassador to the United Arab Emirates, Martina Strong, is going to be flying literally halfway around the world. And I know that because it's a 12-hour time difference. So I just did the math. And she's literally coming halfway around the world. And, the UAE was the host of COP28 this past fall. And so she's got a lot of insights and kind of what went on there, how that's going to impact global energy policy, our energy policy, and her experience. She's a 27-year career diplomat, largely in the Middle East, post in Saudi Arabia, in Iraq, and now in the UAE. So she's got a tremendous perspective on energy, national security, and how all these things kind of play together and how they influence our allies around the world, which I think is a nice follow-up from last year when we had Rahm Emanuel, our ambassador to Japan, and he really focused that on the U.S. and energy as something that builds alliances. And so I think having her as a speaker is really exciting. I'm looking forward to her being up.
Yeah, thanks, Andrew. And I know the governor's also been interested and involved in maybe standing up another rural energy conference to kind of complement some of these bigger picture themes. So I'm really excited to see sort of that balanced focus between both sort of these bigger opportunities for Alaska and then also continuing to pay attention to rural Alaska where we have some of the highest energy costs. So.
Yeah, I appreciate you bringing that up because we do have one of our breakout tracks is entirely focused on rural Alaska issues. Katie Conway from the Denali Commission has been really spearheading that. And then, of course, she's working with the Alaska Municipal League to bring back the Rural Energy Conference, which will take place, I believe, up in your backyard in Fairbanks this fall. The dates, I believe, is early October. I think the COVID kind of put a pause on that, and then our energy conference, and then there kind of was a little bit of not competition or anything like that, but they always wanted to bring it back. So we're glad to work with them on that and help see that come back because rural Alaska issues, it does take more than a breakout track at a conference, so a multi-day event. We are looking forward to that coming back and just helping out with that. And I'm glad you didn't bring it up because Katie Conway has been great in putting together those topics for our energy conference.
Yeah, I know I'm excited about that too. So, I mean, I guess one of the things I'd just like to close with here, Andrew, is sort of going back to that kind of big picture vision for where you see the state going. I know the governor often talks about having Alaska be a place where there's cheap power, where there's abundant energy. And, sometimes it can be frustrating because it feels like progress is so incremental, and sometimes we start to slide backwards too when we see these, gas prices and cook inlet. What is the plan moving forward? The governor still has 2.5 years in his term. So I mean, I know he's thinking about some things moving forward. Can you give us any kind of an inkling on what his big picture vision is for what he's hoping to accomplish with the rest of his term?
Well, I think we all have that sense of urgency. It does start at the top, but we do realize, that time is limited, and we're not going to get to 10-cent power in 2.5 years, but we have to lay the foundation for how we can get closer to that. I mean, I think that it's important to keep in perspective like what just really the challenges are. You could set the fuel cost to zero on the rail belt. You could have natural gas for free, and you would still be over 10 cents per kilowatt hour. So there's lots of issues that need to be addressed, but you have to start somewhere and bringing on, and certainly business wants low cost power, but they also want predictable power. They really need to be able to make economic and business plans that look out 10, 15, 20 years and be able to project that cost of power. And I think that's one place where if you look at things like the hydro, or with renewables that don't have the variability within a gas price, and certainly again we're not trying to get away from natural gas, and if the Alaska LNG project advanced to a point where it was being built, we would have very low cost natural gas available to us in Cook Inlet. So what businesses are really looking for is for predictability. And so that's what we really need to get to, is where we do have stable supply and abundant supply. And the more that we can do, and when you talk about this a lot, is spreading those fixed costs. We need growth. We need more businesses. We need those anchor tenants like, Kinross and Apogo that really contribute to lowering costs in Fairbanks, which I know are still high. I don't want anybody to think that I'm saying they're low, but those large industrial users do help lower the burden for Golden Valley. And so that's where the governor's looking is, where can we find and attract businesses that will become large anchor tenants? How can we find technology that can have long-term, predictable, stable costs? Because businesses really need that. I think if you look at average price for the country, it's around 14 or 15 cents. But if you can remove that variability and instability, where you look at like an imported LNG and what kind of volatility that could introduce into prices, that is the situation that everybody is trying to ward off right now. So if you look at where's the governor's vision, it is to grow this state. It is to bring private sector investment into this state, because all of that can work together to bring those costs down for everything, not just energy, but that will lead to lower food prices, lower housing prices, more services and population. So I think he really wants to see this state grow and take advantage of its opportunities, and which are, virtually unlimited.
Thanks, Andrew. I appreciate your time.
I'm glad to be here. I guess, like I said, I have potentially a little extra free time today based on where house finance is. So.
All right. Well, I'm glad you were able to join us. And so, Brittany, I think I'll turn it back over to you to close us out.
Great. Thank you so much to both Gwen and Andrew for joining us and closing us out for today's workshop. Thank you so much just in general to all of our presenters and panelists for sharing your time and your expertise. This workshop would not have been possible without you, and we sincerely appreciate it. Also, a big thank you to all of you for joining us for the Transmission and Distribution, the Clean Energy Transition Secret Weapon virtual workshop, sponsored by the University of Alaska Fairbanks and the Alaska Center for Energy and Power. The recording of this workshop will be available on the Alaska Sustainable Energy Conference website at alaskasustainableenergy.com in about a week. Please continue to check back for more information. As a reminder, you can also view previous recordings at the same location. We'll also be sending out a short survey following this workshop and would love your feedback. You can access the survey by scanning the QR code on the screen now with your camera phone. We'll also drop a link in the chat. As a reminder, everyone who completes this survey will be entered to win one 3-day conference ticket to the Alaska Sustainable Energy Conference in May. The winner can select either an in-person or virtual ticket. Please take a moment to get your short survey submitted to help the planning committee improve future workshops. We appreciate all of the incredible presenters and virtual attendees. Coming up next, be sure to check out our third and final workshop for 2024, Betting Big, Investing in Emerging Energy Technology, happening virtually on May 7th and 8th. New Zoom links will be sent out for that workshop, so please keep an eye out for that attendee packet. Of course, we hope to see you all in person or virtually at the Alaska Sustainable Energy Conference at the Denina Center in Anchorage on May 21st through the 23rd. Both in-person and virtual tickets are available for the conference, and we hope you'll consider joining us. They can be purchased now at alaskasustainableenergy.com. Once again, thank you so much, and we look forward to catching you next time. Have a great rest of your day.